All right. So just, I recognize a lot of faces, but how many people were not here yesterday? Okay, only a couple. So I'm going to do a very quick review of yesterday, which I'll try to do it in about 15 minutes. It took the whole day, just to give those of you who weren't here just a sense of where we were, and then we'll get into the meta-analysis. Right. So here's an overview of the day. Start off with an overview of systematic reviews and meta-analysis. Again, just kind of a review of yesterday, and then we'll get into various aspects of setting up the data, looking at the types of outcomes you can meta-analyze, talking about meta-analysis as a weighted average, more on heterogeneity. Then we'll get into some of the models, 1- and 2-stage models for meta-analysis, bit on meta-regression. I'll hopefully get a chance to say something about Bayesian modeling for meta-analysis, how you deal with observational data, how that's a little bit different from trials, individual participant data, and if I've got some time, I hopefully can get to multivariate and network meta-analysis. One of you mentioned single case designs. I'm actually doing a lot of stuff in single case designs, and I can say a few words about those as well. But basically, a single case design is when you do a randomized experiment on one person, and they're repeatedly measured back and forth on A and B, and so then you can just put those single cases together and think of each person as a trial, and so then it becomes a meta-analysis. So the principles apply. The only complication is, of course, because you have these multiple measurements on people, you have multivariate data, and you've got time series, and so it becomes a little more complex to model. But I actually have some slides on that. If I get some time, I can dig those up. Okay, so again, a lot of these slides will be just repetitive from yesterday. Systematic review is the general area where we're trying to put together all the evidence. Meta-analysis is the quantitative analysis of that data. And so the idea behind the systematic review is that we're using a protocol and scientific principles to collect all the information that's available on a certain topic. And so it's very important to have a focused question. We talked yesterday about how to formulate a good research question. You want to have a documented, transparent process. You want to, and the nice thing about systematic review is it's a scientific methodology, so it has theoretical and empirical support. It provides a rigorous evaluation of evidence. It minimizes subjectivity and bias. And of course, it involves stakeholders who are the people who are interested in the outcomes of the meta-analysis and who can contribute to making sure that it is done in a way that it's most impactful. And so the process, we saw this picture several times yesterday, the process here running from left to right is that you prepare your topic by defining the questions using the PICO criteria of population, intervention, comparator, and outcome, together with the study design. Once you have that formulated, you then consult your local librarian or your local methodological expert who knows how to search the literature. You put together a search strategy, you go through various databases, and you might do some hand checking of other gray literature, and you find all the articles that appear to be relevant. You'll have a lot of articles that are not relevant, so then you have to screen through them, read the abstracts, read the titles, figure out which articles are pertinent to your question and which are not. And then those articles that you think might be pertinent, you go out and get those articles. You then look at them and screen out more. Now, when you've got your corpus of papers that are going to be part of your study, you now go to read each one and you extract data into a form with all the information you need. And once you've done that, then you assess each study for its risk of bias, looking at its quality. You then do a qualitative and/or a quantitative synthesis of the data, and then you report your findings, right? So that's the summary. So today we're going to be concentrating on this analysis piece, right? So I'm going to assume that you've done a proper search, you've got your articles, you've collected your data, you've extracted it properly, and in fact, we're going to just be talking about how to analyze the data at this point. All right, so as I said, there's a qualitative part and a quantitative part to the synthesis. The qualitative part is basically just to take a broad look at what you've got and try to summarize what's there. Sometimes you won't have enough data to do a meta-analysis, a quantitative synthesis, and so a qualitative synthesis is all you do, and you basically just run through the literature and explain what you found and try to explain how that applies to the question that you're answering and to the audience that you're trying to address. So if you have enough data, then you would want to do a meta-analysis or a quantitative synthesis. And the idea behind the meta-analysis is that you're going to do an analysis of the studies that you've collected for a variety of potential purposes. You could be doing a comparison between two or more groups for some outcomes. You could look at different study effects. You can estimate the differential between the two groups in terms of its effect size and its uncertainty. You can use the meta-analysis to put together smaller studies to come up with a more definitive answer. In particular, if you have many small studies that are all trending in the same direction, but they're too small by themselves to be significant, then one of the conclusions that's often reached in an overview is that there's no evidence for this effect. But of course, if all of the studies are trending in the same direction, there actually is some evidence. And by doing the meta-analysis, you put all that information together and come up with a more precise answer. You can also use the meta-analysis to explore heterogeneity, differences among the studies, why some studies are more positive than others. And we'll talk about how to do that and explain discrepancies when some studies are positive and some studies are negative. You can also use it to examine potential biases and evaluate their effects. So you can try various sensitivity analyses and say, for example, if I exclude the low quality studies, do I get a different answer? If I exclude the studies that are not randomized, do I get a different answer? And so forth. And the other thing you can do is you can identify where the research gaps are. So where is there a lack of evidence? For example, you might find that the study, if you're studying a reading program, you might find that those students who are coming in with lower reading scores to begin with seem to be progressing better than the students who come in with higher reading scores, but you might not have enough data to really support that, and so you might say we need to do more studies stratifying on those two groups. So the meta-analysis that we're going to be talking about today is not always appropriate, and so there's a lot of reviews in the literature that are systematic reviews that do not have a meta-analysis. So why might you not be able to do a meta-analysis? Well, the most obvious reason is you don't have enough studies, because remember, the sample size in the meta-analysis is the number of studies. So if you've only got 3 or 4 studies, you're not going to be able to do much statistically. Secondly, the studies that you found, you may have a lot of them, but they may not be very similar. They may be quite different, and you might feel uncomfortable combining them because you don't really know what that summary answer is going to mean. Third, you could have a bunch of studies that are all looking at the same thing, but they're reporting the outcomes on different scales. So we talked yesterday about how various patient-centered scales, when you respond to a questionnaire, a lot of times there are different ways of asking those questions and different scales are available. And so people may have answered basically the same types of questions, but in different ways, and those scales may not be easily transferable. Fourth, you might have a bunch of studies that are very methodologically diverse. In other words, some of them are randomized, some of them are non-randomized, some of them are blinded, some of them are not blinded. Some of them use controls, some of them don't use controls, and so it's going to be difficult to combine those together. Another reason would be that if you have a bunch of studies that you've collected over a period of time, the studies that were done a long time ago may be very different from the studies that are done now for a variety of reasons, and you might feel uncomfortable combining those together. And then finally, there's a whole bunch of times where you are really, you're just kind of trying to review the literature and get a sense of what it looks like and what the theory is and what the programs that have been studied are, and there's not really anything that's measurable that you can actually synthesize in the meta-analysis. So in that case, what you would do is summarize each study separately and comment on how the results inform the questions of interest to you. I'm not going to say anything more about qualitative synthesis today. We're going to concentrate now on quantitative, but I just wanted to let you know that it doesn't always work out that you can do a meta-analysis. Okay, and then finally, we talked yesterday about the PICO-D formulation, where we talked about the first letter P stands for population. Who's involved in the meta-analysis? Who are you studying? What's the population? What are their characteristics? What are their demographic features, or whatever group you're studying? If it's in health, what's the stage or severity of the disease? If you're in if you're doing a study in biology, how old are the organisms, or whatever the characteristics are. In interventions or exposures, what are they? How are they used in practice? What are the relevant comparators? For the comparators, whether these are no treatment comparators, placebo comparators, active comparators, current standard practice, some kind of gold standard. And then for the outcomes, what are the outcomes? Are they primary or secondary? How are they going to be measured? Are they binary, ordinal, continuous, and so forth? So all of these questions would be answered, and you would extract this data from your papers, and then you can use that information in your meta-analysis. So obviously, the outcome form is going to drive what kind of analysis you do. You do one kind of analysis for a binary outcome, another kind for a continuous outcome. If you have these other characteristics, then you may want to look at what those characteristics, how they might affect the results of your study, and these might be subgroups that you stratify upon. And then finally, the study design is going to drive things as well, because as I said, you might, for example, have randomized and non-randomized studies. You might have studies with long-term follow-up and short-term follow-up, and those again may be things that you need to subdivide into. Okay, so let me just conclude here by saying that we're going to be talking about both randomized and observational studies, or experimental and non-experimental. The principles really apply to both. Obviously, one of the advantages of the experimental or the randomization is that you have the randomization, and so you're able to get rid of confounders and bias. And so it's a lot easier to put things together when you don't have to worry about confounders. But I'll have a few words to say later about observational studies. Okay, that's sort of a real quick review of the non-statistical stuff that we did yesterday. Any questions? Okay, I was trying to get through that fast because we've got a lot to cover, and I didn't want to spend too much time going over stuff that everybody's probably seen before. Okay, so again, we talked about this a little bit yesterday, but now we're going to get into a little more detail. So a meta-analysis typically gets information from a paper. The outcome in a meta-analysis is typically not the primary outcome in the study. It's typically the comparison or the statistic that's calculated in the study from the outcome. For example, if I'm comparing two groups for a particular outcome, then my outcome is not the average in each group. The outcome for the meta-analysis is the difference in the means, let's say, for the two groups. And the standard error or the standard deviation is not the standard deviation of the group values of the outcomes in each group. The standard deviation would be the standard deviation of the difference. Okay, so, but again, you can have different types of outcomes. If you have binary or categorical outcomes, then typically the statistics will be things like proportions or prevalences if you're dealing with one sample, one group. If you have two groups, they might be things like odds ratios or risk differences. If it's a continuous outcome, then the comparison will usually be a difference in means. It could be a ratio of means. You could also have correlational data. So oftentimes we'll look at studies where we're associating two variables and we're interested in the correlations. This is very common in educational data, for example. We can also look at standardized mean differences. What the standardized mean differences is you take the mean difference between the two groups and you divide by the standard deviation in the, let's say, the control group. And the reason for doing that is because if you have two studies that are measured on different scales, then the difference in the means will be on different scales as well. And so to standardize those scales, we're standardizing by the standard deviation. So now you can talk about the measure in terms of standard deviation units. So we'll talk a little bit later about dealing with those kinds of data. There's other kinds of data that are not as common in meta-analysis, but you do run into them. Times to event are very common in certain areas, particularly health and actuarial science and so forth. And so you would look at things like survival probabilities or hazard ratios or median survival times. Sometimes we'll have count data, in which case we might have things like incidence rates or incidence rate ratios that we want to combine. If we have a diagnostic test, we might be looking at things like sensitivity and specificity or odds ratios or ROC curve areas. Right? So these are all the different types of study summaries you can combine, and there's more than those as well, but these are the standard ones. Okay. Now, as I said, most of the time we're combining data from study level data, summary study level data from papers. But sometimes we might be lucky enough to have the individual databases on which the studies were run, in which case we have individual participant level data. We know, for example, not just the average age of everybody in the study, but we actually know the individual ages of the participants. And with that, of course, you can do a lot more analytically. It's hard to get such data, and you know, they are more of a gold standard. However, usually, unless you kind of control the data yourself, you might have a lot of studies in your institute that you've run and you want to meta-analyze them, and you might be able to do it this way, but otherwise you're going to have to go outside and get data from other people, which tends to be more difficult to do. Okay, so a little bit more about summary study level data. Typically here now the outcomes are things like means per treatment group within a study, and we would look at the difference in the means as our meta-analytic statistic. With randomized data, then these study level differences are unbiased for the true differences, although of course they can have heterogeneity because of variability. With non-randomized data, however, the study level differences may be biased because the study groups may be different at baseline, basically, right? Because there's no randomization. So you might have, for example, more men than women in one group, and so that might, if gender is related to the outcome, then that might actually not give you an unbiased estimate of the true difference. So in those cases, some studies may adjust for those confounders, and you might get an adjusted statistic from the paper, and you might be able to use that. But not all studies are going to adjust, and not all studies are going to adjust in the same way. So some studies may adjust for age and sex, and others might adjust for race and income, and so forth. And so those may or may not be comparable. Okay, question?
The previous slide you mentioned summary and persistent level. You did both. Did you get appreciably different results, or are you guaranteed to get the same results?
So there's a few papers in the literature on this, and basically under certain sort of standard assumptions. I mean, if you have the right model and you have the right statistics, then you're going to get the same answer. Obviously, with the individual level data, you're going to be able to look at some effects that you couldn't otherwise do, and I'll talk a little bit later about this idea of aggregation or ecological bias, where the summary level statistic is actually different from the individual level statistic. So there's some things you can't estimate with one that you can estimate with the other, but basically for the standard statistics, yes, it kind of works out the same either way. And in fact, that's one of the ways you can talk about 1- and 2-stage models a little bit. So in the participant level data, we have the raw data with the outcomes recorded by treatment group in person with person level and study level covariates. So if you have binary outcomes and all you're interested in is combining the 2x2 tables that you get from each study, you don't care about covariates, then in effect, if I give you the 2x2 table, you have all the data you need to construct the sufficient statistics for the individual level data, right? Because it doesn't really matter which person has which event. It's the model's agnostic to that because the people are exchangeable within groups. But if you start going into covariates and you want to adjust for them, then you would need to know all the subgroups. So for example, if I wanted to adjust for male and female, I would need to know the number of events per group in males and in females, and you oftentimes don't have that level of detail in papers. So you would not be able to do the individual participant level analysis for that. And so, but when you have continuous or survival type data, or when you need to do regression, you're going to need to probably get the data sets from the individual studies and put them together. And that can be quite cumbersome. Okay, so as a summary here, meta-analysis is going to quantitatively summarize results from different studies, and we'll talk about ways to do that. There are a lot of different types of study results that can be combined, and we're going to use summary information from studies or data from individual participants if available. Okay, so that's the end of the introductory section. Is there any questions on that so far? Okay, so let's move on to metrics. So again, a lot of this is going to be a review. I just want to set up. So I'm going to try to show you here what are the different types of summary effects that you can use in a meta-analysis and how to compute an estimate and a variance for these effects. So the first one we might want to think about is a mean difference. Let's say we've got two groups and we have a continuous outcome. Like let's say we want to compare scores on a test between two groups who are getting two different interventions. So we're going to take the mean in each group and we're going to take the difference in those means as our effect. So there's a slight complication because your study may be longitudinal in the sense that you may have a baseline measure on those folks and you may have a follow-up measure on those folks. So baseline is before the intervention, the follow-up is after the intervention. So in the control group, these should be fairly similar, but in the intervention group, you might expect a change. And so therefore, we would need the statistic there would be a difference of differences, right? We would take the difference of baseline to follow-up in each group and take the difference of those differences. And so we would need to calculate a standard error of that in order to be able to do our meta-analysis. Okay, so let's say we have a setup where we have a treatment group and a control group, and we have a pre-measurement and a post-measurement. And so we're going to take, we would take a mean difference. Now, if you don't have a pre-measurement, if you just have one measurement, you're just taking the difference between the two groups at whatever time point you have. If you do have the pre-treatment groups, then you're going to take a difference between the pre and the post in each group. That will give you a within-arm change, and then you'll take a difference of those two differences to get the net difference. All right, so that would be your statistic of interest here. So as an example, let's say we had in the first group, we had 100 individuals, and the mean post score was 130, and the standard deviation of those scores was 40. And in the other group, we had 101 individuals with a post score of mean of 150 and a standard deviation of 50. The mean difference is then going to be the difference of 130 minus 150, or a 20-point drop. And the variance of the mean difference is just going to be the sum of the variances. And that's just, you just calculate that out with those numbers and you end up with a standard error of the mean difference of 6.4. So in other words, you have a 20-point change and a standard error of 6.4. And so that's a pretty big change because that's about 3 standard errors. Okay, so this is just basic statistics, nothing new here. Now let's make the problem a little bit more complicated in the sense that we now have a pre and a post measurement. So we're first going to take the difference between the pre and the post in each group, and then we'll take the difference of differences. So in the treatment group, the change is 130 minus 160. We can calculate the variance of the change by this formula, and you'll notice that we know it up to one number, which is the correlation. So this is the complication with change data, is that because you have two measurements on the same individual, or in individuals in the same group, you need to know the correlation between the measurements, right? So there's a correlation here because you're taking repeated measurements on the same person. And the problem is that a lot of times we will be given these means and these variances or standard deviations, but we won't be given the correlation in the summary report. So as we talked about yesterday, one thing you can do is you can try to contact the investigators of the study and try to get that information. They may have it. But a lot of times that's not going to be available. And so what we will do instead is we'll try to do a workaround. We'll try to either guess a number here or use some other data to calculate it. Now, it might be, for example, that some of the studies that you have give you a correlation and others don't. So a very crude thing you could do is you just take the correlations in the studies you have, average them, and just say that's the correlation in the studies I don't have, and just impute them. That doesn't work too badly. You would do the same thing in the control group. Again, you need the correlation in the control group. And then when you go, I'm not going to go through these formulas because you can go through them on your own. Then you take the difference of differences and you take the variance of those differences, which is going to, again, be the sum of the two variances and minus 2 times the correlation. But since the two groups are independent, the correlation now is 0. So again, this variance that you need is known up to these two constants, these two correlations. So what you can do, as I said, is you can either use previous data to estimate the correlations. You may know that, for example, in the treatment group, the correlation, or in this kind of study, let's say these are reading tests, and let's say it's a test that's given at the beginning of the year and the end of the year, and you may know from previous data that there's a 0.5 correlation between those two scores. So you might just plug in 0.5. Or you can just take, you can take a good guess. And so oftentimes have some intuition about what these numbers are. And it doesn't, the answer doesn't tend to be too sensitive to what you guessed there. But again, what you can do is try different correlations if you're worried about it and see if it makes a difference in your answer. All right, so that's basically what we do with continuous data. We take mean differences or difference of differences. Now, as I said, sometimes you don't have the values on the outcomes are not on the same scale. So, question.
Is it good to do a sensitivity analysis on your guesses?
Yeah. I mean, so I would try, for example, you could try correlations between 0.1 and 0.9 and see if it makes a difference, right? Or over some reasonable range, right? A lot of times the effects are so big or so small that it doesn't really make a difference. So now let's say that I've done, again, let's say I'm doing a reading intervention, and I have one group of studies that used one reading test and another group of studies that used another reading test. So now the scores that I get may not be on the same scale. So now what do? I can't really combine these scores in this way because some of them, they may have different means in general because of the way they're scaled. So here we're going to define the standardized mean difference as a ratio of the group difference to the standard deviation, so that we can have the effects on the standard deviation scale. And therefore, it's a dimensionless statistic so that we can compare across different outcomes. Now, the problem with the standardized mean difference is that it's hard to interpret the results because you're now talking about standard deviation units. And so while you can talk about whether there's a big change or not, it's not necessarily going to be very interpretable. So, for example, you might have these two reading tests, and you might say, well, this particular meta-analysis shows that there's a 2 standard deviation change on average, and that's a big effect. But unless you kind of know what 2 standard deviations is on each test, you don't really know how many points that is and how much improvement that is. So this is much more frequently used in social sciences than in the health sciences, in my experience. And that's because the social sciences, I think, tend to have many more types of data where they would use different scales, or they might have different measures. Whereas in the health sciences, we tend to have outcomes that are, for example, things like blood pressure, which are all measured in the same way. Also, I think in medicine and health, people are less willing to combine things that are on different scales for some reason. But we do see them oftentimes with patient-reported outcomes where people are asking about quality of life because those scales are not always standardized. So again, the standardized mean difference is the difference in the means divided by a standard deviation. And so the test statistic here would be the difference in the sample means divided by the sample standard deviation. And usually we take the sample standard deviation as the standard deviation in the control group. And then there are various fix-ups to this, because if you have small samples, these statistics are not estimated particularly well. And so there's a whole literature on how to do corrections for the standardized mean difference. And probably the most common one is called Hedges G, where you basically multiply the D, the Hedges D, or the Cohen's D, I think it's called, the D statistic, you multiply it by this constant AN, which is a small sample correction. And Larry Hedges has shown that this has good properties. There's also other estimators. There's a maximum likelihood estimator, there's a shrinkage estimator, and so forth. You can calculate what the variances of these statistics are. So this is the variance of the D statistic. If D is pretty small, then you can sort of get rid of the correction factor and just take the usual sum of the inverse sample sizes. So there's books on this stuff, and you usually if you use software these days, for example, the Metaphor package in R, or Stata has a lot of routines for meta-analysis as well. Those are the two that I'm most familiar with. These statistics are there for you automatically, so you can just choose which statistic you want, and it will do all these calculations for you. Another common statistic that's used with with continuous data are correlations. So we might have the correlations between different tests, for example, maybe a reading test, a math test, a science test across different studies, and we want to somehow combine those correlations. So a typical approach is to take the Fisher transformation, which is variance stabilizing, and work with a Fisher scale. This works pretty well with one sample. It doesn't work as well in a multivariate case because the variances are hard to compute. But the variance here, of course, is independent now of the correlation, and so you don't get that potential bias involved. And then you can use the inverse variance weighted test statistic to get the variance, and so you would use this correlation estimate with its variance. And again, I'll show you soon when we start into the modeling how you actually use these statistics and their variances to actually get estimates. For proportions, you have a variety of choices. So if you're looking at one sample, you would just take the proportion and combine those, maybe on the logit scale. For multiple groups, you might take a risk ratio, risk difference, or something like that, or an odds ratio. So the scale that you choose, of course, is obviously what is of most interest to you. So if you choose a relative scale, like a multiplicative scale, you're basically assuming that you believe that the studies are fairly consistent on the multiplicative scale. If you take an absolute scale, then you're assuming that the studies are very consistent on the additive scale. For example, if I have a health outcome and I want to see whether if I treat somebody one way versus treating somebody another way, does it improve the outcome? I might, for example, in the control group, expect to have 5% of the people have this condition, and I'm hoping maybe that the treatment will reduce it. And so the question is, does the treatment reduce it in a multiplicative way? In other words, does it reduce it by a percentage amount, or does it reduce it by an absolute amount? So if I believe that the 5% would go to 3%, or the 10% would go to 8%, in other words, the difference is always about 2%, then I would use a risk difference. But if I believe it's a multiplicative thing, like the 10% would go to 5, or the 5 would go to 2.5, or the 2 would go to 1, then I would probably use a risk ratio or an odds ratio. Typically, if the effects are constant on one scale, they're going to vary on the other. So what we always try to do is we try to analyze on the scale that's most consistent, because then we don't have heterogeneity. We try to minimize the heterogeneity across the studies, right? So we want the odds ratios, let's say, to be constant across the studies. So the risk difference is just the difference in the proportions. Typically, with the risk ratio, we'll work on the log scale because it's more normally distributed. So we would take the difference in the logs. The odds ratio is the difference in the logits. We could use an arcsine transformation and so forth. The arcsine is actually the variance stabilizing transformation for the proportion. So the nice thing about that is that the variance doesn't depend on the unknown proportion. Now, one complication that you run into a lot of times with binary data is studies with zero counts. In other words, if you have a small study and the prevalence is pretty small, then you might have no events in one or both groups. And so that's problematic because if you're working on a multiplicative scale, you're going to end up having to divide by 0 sometimes. And so you're not going to have a defined odds ratio or risk ratio. So for example, here, in this particular 2x2 table, we've got A, B, C, and D as our 4 counts. And so the risk difference is calculated here as A over A plus B, or C minus C over C plus D. But if A or C are 0, right, then it really doesn't cause a problem here because we're just taking a difference, right? We're just subtracting off 0. However, if on the log scale, if it turns out that you have a 0, then you have a log of 0, and then you don't have a defined number. And so typically, what do we do in this case? The typical thing to do is to add a half to each cell, right? So if you add a half to each cell, then you are able to do the calculation, and it doesn't introduce much bias into your estimate. But this can also be problematic if the counts are really small, or if the denominators are small, because adding a half can then cause a big change. So there's, again, a huge literature in statistics on these continuity corrections, and oftentimes other constants other than a half are suggested. One way around this is to do some kind of a Bayesian analysis. If you do a Bayesian analysis, which I'll talk about later, then you can sometimes put prior distributions on things and you can get rid of this problem with zeros. But it typically is an issue. And then for each of these measures, there's a variance estimate. So for some of these are exact. For some of them, they're approximate. So typically with the log risk ratio and the log odds ratio, you use some sort of delta method transformation to get an estimate of the variance. And so, for example, with the log odds ratio, the standard variance estimate is just the sum of the inverses of all the counts, 1 over A plus 1 over B plus 1 over C plus 1 over D. You'll notice that the variance estimates in the left-hand column there all involve P except for the arc sign. That's why it's the variance stabilizing transformation, because all of the other metrics, the true variance is really a function of the unknown parameter, parameter P that you're trying to estimate. So therefore, you just have an approximate. You can plug in the sample estimate, but it's not an exact. It's a biased estimate. Okay, so as I said, with the 0 cells, we typically would plug in a half to all the cells and do that for whatever measure we're looking at, and then we'll be able to calculate these estimates. So typically, if you have a meta-analysis with lots of studies, or let's say 10 or more, and 1 or 2 of them have a 0 somewhere, it's not really a big deal. There are, however, meta-analyses where many of the studies have 0 counts. So it's a very famous meta-analysis that was done about 12 years ago on rosiglitazone, which is a drug for diabetes, which was I don't know if it was actually withdrawn from the market. I think it might have been for a while. The FDA certainly put a black box warning on it because it was found when somebody looked at a meta-analysis of adverse events of this drug, they found that people who were on rosiglitazone got more heart attacks than people who were not. And if I recall correctly, the odds ratio was about 1.6. So they claimed that the added risk was to increase the odds by about 60%. And there was a lot of uncertainty in the estimate, but it was statistically significant, but just barely. One of the problems with the meta-analysis, though, was they had about 45, 50 studies, but most of them had 0 counts because most of these studies were fairly small and nobody had had a heart attack. But there were a few that did have some counts. And so they did, I think they might have done the half-cell correction. In any case, they did an analysis where it was barely significant. It was quite controversial because this drug was supposed to be very effective in controlling diabetes. And so it turned out that about 20 other meta-analyses of this problem came out, and everybody was writing about different ways of analyzing these data. And it turned out that depending on what sort of assumptions you made, whether you added a half or a quarter, or there were various kinds of Bayesian estimates, various kinds of exact likelihood methods, and it was a very sensitive estimate because there were so many zeros. So depending on how you considered the zeros, you could either find a significant result or a non-significant result. And so it led to a big sort of literature on this. But I think that the main message that I take from it is that in a lot of these cases, the answers are quite sensitive to the assumptions you make, and so you just have to be very clear on what you're assuming. So, in summary here, analyze on the scale that makes the most sense mathematically. So again, I think what you're trying to do is minimize heterogeneity. So if most of your studies have constant odds ratios, they'll have different risk differences. So analyze that way on the odds ratio scale. On the other hand, if the differences are constant, then analyze on the difference scale. And then once you've done that analysis, you can then convert it back to the scale in which you wish to interpret. So if the best scale is relative, then the absolute differences are going to vary with the base rate. Again, if you're dealing with continuous data, then in comparing differences between groups over time, you need knowledge of the correlations. And if you don't have those correlations, you can either try to guess what they are, use previous data, or do a sensitivity analysis. And the weighting and interpretation of the results may change substantially depending on the metric you use. All right. So again, it's like any statistical analysis. There's an old book that I used to read called How to Lie with Statistics. You can always come up with a different answer using a different method, right? And the key thing is you want to be very obvious and clear on what you've done, right? So that if somebody thinks that you're trying to manipulate the data, you can defend yourself. There's, you know, I've done a lot of clinical trials, and the last few that we've written up, and they've been published in very good journals, but we've had this problem of missing data where some people don't respond. And so, you know, the reviewers always want to know, well, what did you do with the missing values? And of course, there's a lot of things you can do with missing values, but let's say one of the things we did was multiple imputation. And what happens, of course, is that you get one answer when you do the multiple imputation, you get another answer when you do the standard analysis. And unfortunately for us, at least with the reviewers and the editors, one answer had a p that was greater than 0.05 and one had an answer that p was less than 0.05. And even though we try to teach people that p of 0.05 is not the, you know, the be all and end all, it still is with a lot of journal editors. And so we get a lot of grief from, well, you're claiming something that's not really true, right? So the thing is just to be transparent and try to make an argument for, you know, why something should or shouldn't be claimed. Okay, what, any questions at this point? Yes. Mm-hmm.
I'm curious, I'm thinking about a lot of studies will have multiple measures of, say, condition in response to the treatment. And those multiple measures may give the same
Right.
And so you measure them all in the study.
Right.
Some are more sensitive than others. And maybe some studies have some sets of those measures and other ones that and I can imagine that you could try to hopefully they all stay on and come home. But you could also focus on kind of multivariate change in this group measure to look at it.
Right.
So talk a little bit about how.
Yeah, so I mean, I'm going to say a little bit later in the day, talk about multivariate analysis. So that would be a case where your focus really is on the outcomes, but you want to adjust for the correlations. The data I was talking about here is more where you have different outcomes and you really are interested in the correlations among those outcomes. So it's not just that you're really interested in one kind of outcome that is measured in different ways. But for example, in education, you might be interested in what's the correlation. If you did, so let's say you tried some new kind of intervention and you wanted to know how it affected the reading scores and the math scores. So you're interested in how those things were correlated with each other. Then, you know, it's not that you're analyzing them separately, but you're actually interested in the correlations between them, and you want to meta-analyze those correlations. Yeah. Okay. All right. So so moving on then. So now we've talked about the different metrics, but I haven't really told you how you put those together. So if you have a bunch of odds ratios, you have a bunch of means, how do you actually put them together? So now we're going to talk about averaging. So I'm going to tell you about different methods for weighting study results to obtain combined estimates and how to interpret forest plots. Some of this is going to be a review from yesterday. So you may remember this picture from yesterday. And so I promised yesterday to go into a little more detail on it. So if you recall, the left-hand side is one way that we could meta-analyze data. So in this picture, the rows are studies and the columns are groups. So you have the blue group and the red group. And so one way we could compare the results in the blue group with the results in the red group is we could average all the results in all the blue arms and compare them to the average of all the results in the red arms and get an estimate. The other way we could do it is we could do the comparison within study. We can compare the red group and the blue group in each study to get a green difference over here on the side. So these two are compared to get this difference, and then we average these differences to get an overall estimate. So this is the meta-analytic way of doing the comparison. And if these are randomized studies, this maintains the randomization because this difference here is an unbiased estimate of the true difference because of randomization. And so therefore this is an unbiased difference of the difference, or estimate of the difference between the two, and therefore averaging for unbiased estimates. And so this ought to be a good estimate. Whereas here, we could have problems with confounding because we're now mixing data across different groups, and if these groups are differentially set up, and I'll show you an example of that, this estimate may actually be confounded by study. So I'm going to give you an example of this. This is called Simpsons Paradox in epidemiology. So let's say we have two binary variables that are examined in two populations. So we have multiple 2x2 tables, where each table is a study, or maybe we have one study that's stratified by a factor. So here's an example. We have a study where people were either treated or not treated, and the outcome was whether they lived or died. And we have one set of data for males and one set of data for females. So for the males, there were 297 who got treated, of whom 4 died, and 179 who didn't get treated, of whom 3 died. And when we calculate the odds ratio, we get the odds ratio for males is 0.8, and the confidence interval is 0.18 to 3.57. Among females, there were 25 treated and 2 died, and 214 not treated and 17 died. So the odds ratio turns out to be 1.01, and you get a confidence interval. So if this is the data that you were given in a paper, and you were asked what's the relationship between death and treatment for males and for females, and is it any different between males and females? In other words, is there an interaction here? You'd probably say, well, no, because one odds ratio is 0.8, one is 1. They have wide confidence intervals. There doesn't seem to be any real evidence of the difference here. And so therefore, you might say, well, okay, if there's no difference between males and females, let me just combine all the data together and get an odds ratio for people. So I'm just going to add these two 2x2 tables together. And so this is what happens when I add them together. I have 322 treated, of whom 6 died, and I have 393 not treated, among whom 20 died. And now I get an odds ratio of 0.35 because the treated group has much less death, is much less likely to die than the non-treated group. And now it's a statistically significant result. So looking at this data, I would say the treatment works. Treatment reduces mortality. But it didn't work for men and it didn't work for women. So the question is, why is that happening? And this is Simpsons Paradox, right? The paradox is that you have a statistically significant result for the whole group, but you have a non-statistically significant result for each group, each subgroup. And so the basic problem here is that we have confounding. So if you remember what confounding is when you have a relationship among 3 variables, and you're interested in the relationship among 2 of them, but they're confounded by a 3rd variable, such that all 3 variables are correlated with each other. So here, if we look a little more closely at the data, you'll notice that not only in these studies is there a difference between the death and the treatment, but also there's a relationship between the number of people treated who are male and female. So in the male group, among the males, the majority are treated. Among the females, the majority are not treated. In fact, it's a very large majority. So therefore, when we combine the data together, the overall treatment rate is going to be driven by the male data, and the overall control rate is going to be equally weighted between the males and the females, right? Because they're pretty well balanced. Now, it turns out also that the death rate is much less in the male group than in the female group. So since males are less likely to die, but they're more likely to be treated, therefore the treatment group, when you combine them together, is going to have a lower mortality than the control group. And so that's what's going on. Yes?
This looks a lot like an experiment where when you have a blocking factor that's significant, and when you combine it with the difference in the blocks kind of overshadows the effect that you see when you take up and block this thing.
Yeah, except that usually in experimental design, the blocking factor is going to be orthogonal to the treatment, right? Because you set it up that way. Here, the problem is there's no orthogonality because these are correlated. Right. It would be what would happen like in an experiment if you had a lot of dropouts in one group, and so the dropout was related to the outcome, and so you got unbalanced data, but it caused confounding that way. Right, right. So, you know, a lot of you may be familiar with the Mantel-Hensel test, which is sort of a standard statistical way of analyzing such data. And the idea here is that, you know, if you think of these as two separate studies, the right way, if we go back to our picture, the right way of analyzing this is to do the comparison between the males and the females. Sorry, between the treated and the control in the males and in the females separately, and then combine them rather than combine the data together and then analyze it. All right. Okay, so basically, if you do this correctly, you'll get an average between the 0.8 and the 1.01. So basically, Simpsons Paradox here. If the effect of gender is ignored, the overall strength of association. Oh, that's a typo because that was an old. Example. I got to fix that. The overall strength of association between what I meant to say is treatment and death appears greater than for either males or females separately. And this is known as Simpsons Paradox. And it occurs when the magnitude or the direction of the relationship between two variables is influenced by the presence of a third variable known as a confounder. So in this case, the confounder is gender. And the problem is that gender is related to the probability of getting treated, and it's also related to the probability of dying. So males are less likely to die, but more likely to be treated. And so because that's related to both of the variables you're interested in, it confounds the relationship. So overall, the overall effect of treatment is that treatment is protective. Treatment is related to mortality by itself. But gender is also related to treatment, and gender is also related to mortality. So you have this triangular set of pairwise relationships, and so you get this confounding. Okay, so that's something that you need to be aware of. That's why we do the meta-analysis the way we do. We average within study first, and then we average across studies, and I'll show you ways of doing that here. Okay, so now this is again from yesterday. We talked about the basic idea in the meta-analysis, so we're going to average things. So very simple example here. We have 3 studies. We have 3 estimates of the treatment effect, -6, -7, and 0. And we have 3 confidence intervals, which we could also use to estimate the standard error of each study. So the main statistics we're going to need are going to be the estimate and the standard error. The standard error is for the weighting. Okay, so we talked yesterday about looking at these data, and the question is, if we had these 3 results and we wanted to ask the question overall, does this, let's say this was blood pressure. One study shows that the blood pressure is reduced by 6. Another study shows it's reduced by almost 8. The other study shows no reduction at all. And our question is, well, if we combine all these studies together and look at the evidence all together, can we say there's a blood pressure reduction? And so the problem here is that 2 of the studies show fairly large effects that are statistically significant, and 1 study shows no effect. And so we said that the right answer here depends on how we want to weight these studies. So we could either weight them equally, or we could weight them by the sample size, or we could weight them by their inverse variance, or there's a bunch of ways we can do it. In general, we're just going to take a weighted average. So we're going to take each estimate and multiply it by a weight, W, and then we're going to add those weights up and divide by the sum of the weights to get a weighted average. And so the question is, what is the weight that we use? And basically, if you can just remember this formula of a weighted average, most of what I'm going to be talking about today are different ways of coming up with these weights. All right, so this is a very simple example of it, but basically this is what we're doing. So one way is you could choose the weights to be equal. Each study is weighted by 1/3. And so if you do that, you get an estimate which is just a simple average of the 3. And it turns out that confidence interval overlaps with 0. And so you would conclude here that there is no real evidence of a significant difference, right? That this effect, while it's about 5 points, is not significant. You need more data. On the other hand, if you decided to weight by the study sizes, in other words, you gave a study a weight proportional to its size, then the first and second studies are going to get much bigger weight. And since they have much bigger effects, your overall average effect will be bigger. And it turns out that the variance is smaller as well. And so therefore you get a very significant result. So doing the weighting this way, you say the two studies are driving the analysis, the two big studies, and you would say there's a difference. In general, we're just going to use any kind of weights at all. So we could use very different weights, and as long as those weights are between 0 and 1 and they add to 1, we'll get an answer. So it turns out that the best estimate in the sense of minimizing the variance of the estimate turns out to be the inverse of the variance of each study. So if I take the variance estimate for each study, which I could compute using the confidence interval, and I weight by the inverse of that variance, then that will give me my best answer in terms of minimizing the overall variability of the estimate. And I can do that, and I should have actually provided you here, but I didn't, with what that weighted estimate would be. Now, typically, that's going to be very close to the sample size estimate because the variances, the standard errors of these estimates are typically going to be very closely related to the sample sizes, right? Because the variance of a mean is the individual variance divided by n. So the n is generally going to drive things here. All right, so this is going to be this is probably the most commonly estimated variance or estimated weight is the variance, inverse variance. And there's a connection here to regression. So if you think of the y's as the outcome, and x as the design matrix, and beta as the regression coefficients, with epsilon as the standard error. In this case, we're doing a weighted average. So if you think of the betas as the things that you're combining, and x here is just a vector of 1s because you're just going to take a sum of the betas, sum of the y's. And it turns out if you actually assume that each, I don't have a board here, but if you think of the y's as being arrayed in a vector, so each number in the vector is the estimate for the study. And the variance of each study is the variance estimate for that study. So those would be the weights that you're applying to the error vector. So this is just like a weighted regression. So the variance of the errors, each one has a variance VI. And so the covariance is a diagonal matrix. If you do least squares, then your regression, your estimate beta hat turns out to be this weighted average. The sum of the y's divided by v divided by the sum of the 1 over v's. And the variance of beta would just be 1 over the sum of the 1 over v's. So the beta hat is the weighted average I just showed you, where the weights, so 1 over v is the weight. So that's just sum of y times w over the sum of w. Okay? And then the variance is just going to be 1 over the sum of the w's. So that's the same formula we just showed you. And so I'm just showing you here that you can derive that just from standard weighted least squares regression. It's just a weighted least squares regression. So so a lot of times when people learn meta-analysis, they learn these things as weighted averages. But for those of you who know a little bit of statistics, I just want to tell you that this is basically a statistical estimate. So this is like doing a weighted regression where the weights are known. Now, how do we actually represent this? We talked about this yesterday with the forest plot. So what we would do is we would array all of our studies in rows, and according to each study, you have an estimate and a confidence interval for that study. So for example, if you look at this study here, the dot lines up with an odds ratio of about 0.6, and the confidence interval goes from about 0.1 to 3. And so that confidence interval overlaps with the line of no effect at odds ratio of 1. So that study has a small effect that is not statistically significant. The next, so all the studies that are to the left of the null effect favor the treatment here, which is the beta blockers, and the studies to the right favor the control, which is the placebo. And we're looking here at an outcome which is heart attacks. So what most of these studies are to the left of the vertical line of no effect. And so most of these studies are showing that beta blockers reduce the probability of a heart attack. There's a couple studies to the right, but they're fairly small. So we yesterday, I think we counted up here and we said that there were 5 of these studies were actually statistically significant in favor of the beta blockers. And the remainder, which was about 20, were not statistically significant. And none of the studies actually favored the control in terms of significance. So we were wondering, when we looked at this plot, kind of what was the summary estimate. And it turns out the summary estimate here is at the bottom. And so think about what we just did in terms of how to calculate this summary estimate. We basically took all of these estimates and we took a weighted average of them, where we were weighting by the inverse of their variance. So the studies that are bigger, that have tighter confidence intervals, are getting more weight. And when you average them all up, you get an odds ratio of 0.77. And the width of that diamond is the 95% confidence interval. So it's a pretty precise estimate. And if you remember, the variance of the estimate here was 1 over the sum of the weights, right? So basically, as you're getting more and more studies, the weights are adding up, right? And so the denominator is getting bigger and bigger, which means that the variance is getting smaller and smaller. So basically, when you have a lot of studies, your variance is decreased, and it gets very small. And so that's why you get a precise estimate. Okay. And any questions so far on that? Yes.
So if you were to have one huge study that combined all the people, many people are very knowledgeable, you get something similar to the
Yeah. So I'm actually going to show you an example of that later, where there's a humongous study which just basically wipes everything else out. And it turns out in that particular analysis, it really is very dependent on what your weights are. Because if you choose the weights according to the sample size or the inverse variance, it's going to really favor the big study. And that will drive everything. But if you choose a different type of model, then you get a very different type of answer. Yeah. Mm-hmm. Right. Well, I mean, so I'm going to tell you a little bit about the random effects model, which is kind of a way of getting around that. And basically, what you're assuming is that every study is a random draw from all the possible studies. And so you're basically going to give more equal weights to the studies, because the idea is, well, okay, so I know this one study really, really well, but that's only one possible study. And so I don't know the other studies as well, but they're different. So therefore, I shouldn't just go with this one study. Think about it. Let's say there were 10 possible results you could get, and you did 8 studies, and you got one of each type. And you knew the right answer was to just average those 10 or 8 studies or whatever. Let's say you got all 10. But one of the studies was much, much bigger than the other. Then you'd be saying, well, it doesn't make any sense to weight that study more, because it's just giving me a better estimate of that. But I don't want to let that drive everything, because the other estimates are important too. Yeah. Right. So in that case, you might do a sensitivity analysis by dropping that study out, and now you find there's a different answer if I drop that study out. So it's like with any kind of regression analysis, if you've got an outlier, you have to decide what to do with it, right? You can either say, well, that outlier is different from all the others, and so I'm going to drop it, and I'll summarize and say that I've excluded this study because of hopefully some good reason. Maybe, for example, maybe you'll find that study was the oldest study, and so you just think it's different from all the others because it was done a long time ago. And so you're going to say, all right, well, for all the studies that were done in the last 10 years, here's the answer. If you want to include the one study that was done 20 years ago, I get a different answer. You don't really know what's the right thing, but you're just telling people. Okay, so just to summarize here, so meta-analysis gives you a statistical summary of effects from different studies that's usually based on a statistical model. So the one I've given you here is called the common effect model. And so we'll talk again about the different models, but this is the most standard one to come up with an average. It summarizes the average effects across the studies, and as I said, the most common is a weighted average, and the forest plot is a way to describe the data, display them, and show the overall estimate. Okay, yes, question? No, that would be a predictive mean. This is just the average mean. So what this says, what's the average result and what is the uncertainty in which I know that average? Not the uncertainty in which I know an individual result, but how well do I know the average? So basically, I do a new study, I should expect that new study to be the average plus whatever the random variation is for the single study. So if you think about the new study being those two components, I'm saying now that I know one of them pretty well. I know what the average is, but I don't know the uncertainty very well. Okay, it's just like any average, right? If you take a sample of data and you compute the average, the more data you have, the better you know the average, but you don't know an individual item that well.
Right, and the uncertainty you're displaying there is actually
in the means, right? Yeah, in the average estimate. Yes.
About estimating the effect size for two different studies.
Mm-hmm.
Like if I feel both things are like two ways of data,
Mm-hmm.
but what people are
right. Right. So that's non-randomized data are difficult. Because if they are controlling for different things, then basically you're getting a conditional estimate, but it's conditioning on different things. And so one argument would be that, well, you shouldn't even combine those data because they're basically not comparable statistics. Other people would say, well, presumably if you adjusted for the same thing in each study, the adjustment wouldn't be that different. In particular, let's say that a lot of people do adjustments by variable selection. So for example, they'll try to adjust for 15 variables and they'll leave the ones that are significant in the model. Now that's not necessarily the best way to do it, but that's what a lot of people do. So if you found that one study adjusted for age and sex and another one adjusted for race and income, it might very well be that in the race and income analysis, age and sex were not significant, so they just dropped it out. And conversely in the other study, in which case, if you'd adjusted for all of them, you might have gotten a very similar answer. So you could make the assumption that those adjustments are reasonably comparable, and so those adjusted estimates can be combined. But that's a good thing to kind of note in your methodology and in your discussion, that that's one of the limitations of your meta-analysis, is that you can't be sure that those estimates are really the same thing, because they're conditional means on conditioning on different variables. Yes. Well, so in a study, if your statistic is a mean, right, then you want the standard error of the mean, or the standard deviation of the mean, if you want. So you're using the variance of whatever statistic you're using that you're summarizing. So if it's an odds ratio, you're using the variance of the odds ratio. If it's a mean difference, you're using the variance of the mean difference. And usually those are going to be provided to you in the studies. I mean, if the study just gives you the mean and the standard deviation in each group, but you also have the sample size, then you can calculate the standard error pretty simply. Okay, I didn't understand that. Yeah. Right. Well, so I mean, a lot of times the studies may not give you the standard deviation, in which case you'd have to take a guess. But usually there's enough data there to kind of figure it out. I mean, there might be a confidence interval you can back calculate. When you combine across all the studies, yeah, then the estimate at the bottom will just be the variance of the average mean difference. Does that answer your question? Okay. Yes. This is the standard thing that people use. I mean, there are a lot of different types of graphics that people have used, particularly if you have multivariate data, you might try something else. But this is the standard one that you'll see in the majority of papers, I would say. Yeah. Okay.
Yeah, well, I think mine was similar to this gentleman's part to capture exactly what was happening. The variances of these individual studies
Yes.
is so the difference in differences, the variance of differences. Yeah.
It's a variance of the difference in differences. Yeah. Yeah, it's the variance of whatever statistic you're using to combine.
And if several studies have different, so if there's several studies that use difference in differences, and other ones that are using just straight up
Yes.
comparisons between treatment and control.
Then so then you've got a problem, because now some of your when you're combining, you're not combining the same things.
Yeah.
So that probably you would, I mean, you want to combine. It depends, I guess, on whether you think that the difference in, okay, so if the baselines are pretty much the same, like if it was randomized data so that the baselines were basically the same, then the difference in differences and the difference posts are not going to matter, so you could combine them together. But if they're not, then you might have to think about whether it's reasonable to combine things that way. That sort of issue also happens a lot of times when you combine crossover data with non-crossover data. Or if you have single case data with non-single case data, because now you've got different designs, and so the statistics may be slightly different. Yes? So crossover design is when people get each treatment. So they get A and then they get B, or they get B and then they get A, right? And so those are very standard kind of designs because they're very efficient. You can't always do them because people can't always cross over, but if you can do it, then you will sometimes have data where some of the studies are crossovers and some of them aren't. And there's some papers out there that tell you, how to combine those together, but you basically need a valid estimate of the crossover and a valid estimate of the other study, and then you can combine them together. Okay, so the next section here is heterogeneity. So here I'm going to talk about different types of heterogeneity among studies and how to quantify it. So you'll remember this picture from yesterday, where we have data up top which are coming from different subgroups. So for example, could be males and females, could be people with and without diabetes, it could be people who live in different places. And we said that the idea here is that each study, or randomized controlled trial in this case, is sampling from some but not all of these subgroups, and sampling differentially. So some of the groups are going very heavily into one study and maybe not into others. And then in the end, you're going to combine them all together into the meta-analysis. So you have different subgroups which are representing different different participant characteristics, and different types of outcomes, and and they made up different responses to the treatment. And then you have different inclusion criteria and ways of recruiting people into the studies and random variations. And so you might have different cohorts in each of these studies that are quite heterogeneous. And when these all get combined together into the meta-analysis, there's other issues that might arise, such as bias from publication bias, or outcome reporting bias, or exclusion of some studies in the meta-analysis. And so some of the subpopulations are overrepresented and others are unrepresented in the meta-analysis. And so now this is sort of the overall problem, is that when we do the meta-analysis, when we look at the individual studies, they come up with very different estimates. potentially because they're looking at very different types of individuals. And so if any of this heterogeneity is related to the outcome or related to the differences we're interested in, then we're going to get a lot of different answers. And so the question is, how do we deal with it? Now, there's a fundamental problem here is that we never really know what we've got in the meta-analysis, right? If we've got a bunch of studies, we don't really know how they've sampled from the overall population. Hopefully, we have some idea about what the overall population is that we're interested in. It might be all kids who have a certain characteristics. That's who we'd like to be sampling from. And each study is sampling from some of those individuals, but not others. But we might not really have a very good idea other than, well, we know where the study was done and we know where the people were recruited from. So therefore, we know that if a study was done in Chicago, it's going to be very different from a study done in Seattle, just because the kids are different in those two sites. But if we're interested in generalizing to the whole US population, then obviously having two studies in different parts of the country is not necessarily going to generalize that well. Okay, so here's an example of a bunch of studies where, and it doesn't really matter what this is, one is looking at albumin, one is looking at prostaglandin. These are just two biomarkers. But the point here is just to see that on the left-hand side, all the studies pretty well line up together, right? All the estimates are pretty similar. And one would look at the overall estimate there at the bottom and believe that. Say, okay, well, yeah, that's pretty much an average of those, and it's pretty well estimated because each of the values is pretty similar. And over on the right-hand side, you have much more variability in the sense that some of these studies are positive, some are negative, and some are have a risk ratio below 1, some have a risk ratio above 1. And the overall estimate there, while it's in the middle of all this individual estimates, you might wonder whether that really is representative of any of the studies at all, because it's an average of all of them, but maybe that average doesn't really mean much, because maybe these studies are so different that you can't really average them. It's like saying, well, what's the average height of two groups that are very, very different? That average doesn't really have a meaning. Here's another example, a famous example. So 8 old studies of mammography, screening mammography. In other words, does mammographic screening actually reduce the risk of breast cancer and reduce the risk of death from breast cancer? And so these studies were done all over the world, some of them in Scandinavia, a couple in the United States, one in Canada. And the overall estimated average odds ratio is 0.79, which would say that the screening mammography reduces the risk of breast cancer by 21%. But some of the studies, particularly the top 2, seem to be quite different, and in fact seem to show no effect of screening, whereas a couple of the others are much more significant. And again, the question arises as to, since there's so much heterogeneity here, does this treatment work or not work? And so this data have been analyzed many, many times. I remember going to a conference in NIH many years ago where the investigators were all there and they were all arguing with each other. The guys from Sweden who'd come up with these great results were saying, well, the people in Canada had just done the wrong study and their design was all wrong, and the people in Canada were saying the same thing about the guys in Sweden. And so, but this was really important, right? Because what this went down to is, I think these data are actually related to whether women should get screening in their 40s or in their 50s, and this was a huge deal for a long time as to what was the age to start screening. And so, again, these are all the data we have, and you can sort of pick the studies apart and say, well, they didn't randomize properly, or they had dropouts that they didn't adjust for, or whatever. And when you do the meta-analysis, the answer you get is only as good as the model you choose, right? So if you're going to take a weighted average of these things, then depending on how you're going to weight these, you're going to get different estimates. So when we think about heterogeneity here, we're asking the question, are the studies and effects sufficiently similar that an average effect is meaningful? Or should we be describing different effects in different groups? And this results from variation in the relative differences among treatment effect modifiers. In other words, is the treatment effect modified by other factors? So between study heterogeneity talks about the extent to which individual studies vary from one another regarding the true treatment effect that they're trying to estimate. So in the breast cancer we are trying to estimate the average effect of screening, and so the different studies have different estimates. And this can result from study or patient characteristics, or it could also just result from random variation. Within study heterogeneity means that within each study, the results are variable. So true variation in the treatment effects within studies due to differences in individual characteristics. The issue here, though, is if you only have study level data, you can't estimate the within study heterogeneity. So if I tell you that the, let's see, going the wrong way. If I tell you that, that this study here, this Malmo study, if I were wondering whether this result applied to everybody in the study, or whether, for example, the younger women and the older women had different risks, I couldn't tell you from these data because all I have is the average across everybody. The only way that I could get the individual results by age would either be if I had the results by age somehow stratified that was provided to me in the study in a table, or if I had the individual participant data and I was able to do the analysis myself. Okay, so but you usually are only going to be able to adjust for between study heterogeneity. And so that will cause some issues that we'll talk about later. All right, so there's several different types of heterogeneity here. And so you can think about this as sort of conceptual or heterogeneity that's related to the types of individuals being studied. There's methodologic heterogeneity related to how the studies were actually done. And then there's statistical heterogeneity that's related to random variation. So what are some of the factors that could affect heterogeneity, could cause heterogeneity? So one is that the populations being looked at in each study are different. So every trial has certain eligibility criteria. Some people are allowed in the study and some people are excluded, and those can vary from study to study. And so that could affect your heterogeneity. Also, the conditions that you're investigating could be different. For example, if you're doing a study for to see how well fish stocks are growing in a certain bay, or you might have done one study in one part of the bay, another study in another part of the bay, or one study in the winter and one study in the summer, and so you might get different results because the conditions are different. Geographical variation is another cause. Another reason might be that the actual interventions or controls that you're studying vary. Like one study could have a higher dose or a longer duration, could have longer follow-up time, could introduce different ways of administering the treatment, or the people who are doing the treatment may have different levels of experience, or the type of control you're using could vary, and all of these could introduce variability into your results. And then finally, there could be variability in the outcomes. Sometimes the outcome definition can cause heterogeneity. For example, are you defining something according to one scale or according to another scale, or are you defining an outcome could either be measured with one instrument or measured with another instrument. In terms of methodology, different designs. You could have some studies that are randomized, some that are non-randomized, some that are crossover, some that are parallel group. Studies can be carried on for different amounts of time. So a study that went on for 5 years, the pre versus post may be quite different from a study that went only on for 1 year. And then there's various aspects of how the study is actually conducted. So we talked yesterday about allocation, concealment, blinding, and so forth. Approach to the analysis, what model was used to analyze the data, particularly if you have confounders, or how they handled missing data. Did they use imputation or not? Or other ways that could be related to how the study was actually conducted. And then finally, the statistical heterogeneity. Even if the studies are identical in everything, you still are not going to get the same answer, right? When you run the study twice, if you repeat the study. So that's statistical heterogeneity. And so this could be, this could just be chance variation, or it could be an indication if you estimated that there's some kind of bias involved. so that you get more variability than you think. So what we're basically going to be doing is we're going to be estimating the variability between the studies and comparing that to what we'd expect by chance, by statistical uncertainty. And if it's greater than chance, then we'd say that there's some other factor that's driving the heterogeneity. So it's difficult to identify heterogeneity. And one of the reasons for that is that, remember, the sample size is the number of studies. So think about calculating a variance or a standard deviation. It's really hard to do if you don't have a very large sample size, right? It's not a very well estimated statistic. So this kind of variability is going to be very hard to estimate with only a few studies. So we can do this in a variety of ways. We could visualize the data. And so, for example, if we visualize a forest plot and we find the confidence intervals from some of the studies don't even overlap, then that would indicate that there's potential heterogeneity. We could do a statistical test, and I'll show you one or two of those. But the problem here is that they usually have low power because there's not a lot of data. There are not many studies. And the other problem is that if you have a lot of studies, it's going to tend to find heterogeneity even when it's small. And so it's not a very, very accurate test. And then finally, we could try to quantify the amount of heterogeneity by calculating a variance and looking at various statistics to try to figure out whether that variance is larger than expected. So the standard statistic that's used is called the Cochrane's Q statistic, which is defined here as so K here is the number of studies, W sub I is the weight for the ith study, Y sub I is the estimate for the ith study, and mu hat is the estimate of the mean that you get by what's called a common effect estimate, which is basically the weighted estimate that I showed you before. So we take the difference between each study's estimate, each study's YI, and the overall average, and we square that difference, multiply it by the weight, add them up, and that's the Q statistic. So if you think about what's happening here, if all of the studies are basically estimating the same thing, then the difference between YI and mu hat is going to be small, right? And so this sum is going to be a small number. If, on the other hand, there's a lot of variability, then the weights, then the difference between Y and mu hat will be large, and the sum will be large. So large values of the sum indicate a lot of heterogeneity, and small values indicate very little heterogeneity. And it turns out that if you know the weights, which is a big assumption, but if you know the weights, then and there's no difference, and there's no heterogeneity. The null hypothesis is that all the Y's are estimating the same mu hat, or same mu, then the Q follows a chi-square distribution with k-1 degrees of freedom. So this provides a statistical test. I can calculate Q and compare it to a chi-square distribution with k-1 degrees of freedom and get a test statistic. But the problem is that the test has low power with few studies. And so a lot of times what people will use here is they'll use a more liberal cutoff like 0.1. So if the p-value of this test statistic is greater than 0.1, they would say there's no heterogeneity. If it's less than 0.1, they say there is heterogeneity. This is a little bit old-fashioned now. People don't really use this test. It's not recommended because it has low power, and therefore to decide whether or not there's heterogeneity based on this test is somewhat problematic, particularly if you don't have many studies. But it is still the standard statistic that's used for a lot of the estimates that we're going to talk about later. There's another statistic which is very common. It's called the I-squared statistic. It's been around for about 15 years. And basically what the I-squared statistic tries to do is it tries to say, not that to test whether there's significant heterogeneity, but to try to estimate how much heterogeneity there is. And it's calculated with a formula here, which I've shown you. It's basically the Q number minus the degrees of freedom, k-1 divided by Q. And it turns out that you can basically represent I-squared as a ratio of the variance between the studies to the sum of the variance between plus the average variance within. So tau squared here, we haven't really talked about the random effects model yet. But if I assume that all the studies are different, so each YI is estimating a different mean, then those means, those different means in the studies will come from a distribution which has a variance. And the variance of the distribution is tau squared. So that's the between study variance. If tau squared is 0, that means that the studies are all estimating the same thing. And so I can just take a weighted average. S squared, you can think of as sort of the average within study variance. So each study has its own variance, and this is the average of those variances. So in this case, I squared is a ratio of the between variance to the sum of the between and within. And so it's sort of like an interclass correlation. So if you have much more variability between than within, then tau squared is going to be bigger than S squared. And so this number is going to be closer to 1. If, on the other hand, you have no between study variability, then tau squared is 0 and I squared is 0. So I squared values near 0 indicate little heterogeneity. I squared values near 1 indicate a lot of heterogeneity. And so it's used as sort of a summary statistic that way. And it's thought of as the percentage of total variation in the study estimates that's due to variation between rather than within studies. Okay, so if tau squared is 0, that means all the studies have the same mean, and that would mean we would use a common effect model. And if tau squared is not 0, it would say that all the studies have different means, and so we would use what's called a random effect model, which I'll be talking about soon. So in the old days, people used to do a statistical test, and if it came up significant so that there was heterogeneity, they would use the random effects model, and if it came up non-significant, they'd use the common effect model. But nowadays, it's sort of thought that, well, there's usually between study variability in any case, and so we usually use a random effect model these days. All right, so the other nice thing about this statistic is that it's not reliant on the number of studies in the meta-analysis, so you can compare it between meta-analyses. So if you have two different meta-analyses, one of which has an I-squared of 0.4 and one of which has an I-squared of 0.6, then you can sort of very colloquially say that one has more heterogeneity than the other. So what do we do with heterogeneity if we find it? So we talked about this a little bit yesterday. We can do several things. We can either ignore it and sort of use a common or equal effect model, just assume that all the studies are estimating the same thing. That's probably not a very good idea, but sometimes people will do it. We can try to estimate the uncertainty, estimate the tau squared, for example, or do a statistical test, and then say, well, if there's heterogeneity, then these studies are all different, and I don't want to combine them. Or we could try to account for the heterogeneity by using something like a random effects model and get a random effects estimate. Or we could try to explain the heterogeneity by using some kind of a regression model to try to explain how those variations in different factors might affect the estimate. All right, so we'll be talking about the equal or common effect model, the random effect model in the next section, and then we're going to talk later about meta-regression as well. So a summary here is that study results can vary because of different objectives, different design, different analyses, and exploring the heterogeneity among the results can illuminate the reasons why the results differ, thus enhancing your understanding of the problem at hand. And various graphics and statistics are useful in quantifying the heterogeneity. All right, so there's a lot of different ways of calculating these estimates, and I'm going to show you some of them, but this is a whole cottage industry. There's papers being published all the time on different ways of estimating these things. Should we do one more, or do we want to take a break? Okay, question. Yes. Yes. No, I'm just taking some sort of an average of them. It could maybe a median or a mean or something like that. I mean, basically, if you assume that they're all the same, then you can show that that I squared is equal to this. So the sort of intuition is, well, if you just take an average estimate and plug it in, then this is pretty close to, I mean, it's not exact, but it's an approximate. Yeah. Yes. There are cutoffs that are suggested. I don't tend to like to use them because it's kind of like the effect sizes where, people say if it's 0.3 or less, it's low effect size. I mean, generally, if it's above 0.5, it's 50%. It's probably a lot. But you know, some people would say that any heterogeneity should be adjusted for. I typically just use it as a descriptive number because I typically will use random effects models anyhow, because I just don't believe that most studies are estimating all the same thing. So, okay, any other questions? Take a break? Okay, good. 10:25, 10:30? 10:25, okay. Okay, I will put my lay on. So before we get going again, since the next section is going to be fairly statistically heavy, I just thought I actually sent this to a friend of mine the other night, but I thought you might, if you're feeling a little lost, at least you'll feel like you're not as bad off as some people. So in a recent poll of 3,200 people, 56% of Americans responded no to the question, should Americans as part of their school curriculum learn Arabic numerals? What? Be forced to, yes, yes.
That's the key.
That's,
nobody wants to be forced.
Yeah, right.
Sorry.
Yeah, no. And 50, well, what I loved was 15% had no opinion, so, you know. Okay. So the next two sections, I'm gonna go over these models that we've talked about. And the first module is the two-stage model, which is kind of what we've been talking about. And so here I'm going to tell you the difference between the common, or sometimes called the fixed effect model, and the random effect model, and how to use those to calculate estimates and average effects. And also, very importantly, to know when the assumptions in the models may or may not hold. So what is a two-stage model? The two-stage model is basically what we've been doing so far, which is the first stage works within study to get an estimate of whatever statistic you're interested in, like a mean difference. And then you also get a variance estimate. And then you take those estimates and you combine them together in the meta-analysis. So the second stage combines the study estimates via a meta-analysis model. Right? So first stage is to use estimate in the study. Second stage is to use the meta-analysis across the studies. Now, there are a variety of different models you can use. And the terminology here is a little bit confusing. So I'm going to tell you about three models, which I'm going to call the fixed effects model, the common effect model, and the random effects model. The common effect model, and notice that it's in effects, not effects. There's no plural there because it's only one effect, is sometimes called the fixed effect model, also, confusingly. That's actually more common in literature, but we're trying really hard to change this to common effect, and I'll tell you why, because it contrasts with standard statistical terminology. It's also sometimes, unfortunately, called the fixed effects model, but it's actually one effect. So just as a terminology issue. Now, the point is that these are all estimating a single average effect. And so these may not be reasonable if there are particular moderators that affect the estimates. For example, there's subgroup effects that really are more important than an individual overall average. All right, so what's the fixed effects model? So the idea here is that you have an estimate, you have a sample average, let's say average difference yi in each study, and let's assume that that yi follows a normal distribution with a true mean theta I and a variance vi. So yi is the observed effect, like the mean difference between treatments. The fixed effects model says, and if you remember in statistics, fixed effects apply to things where there's no relationship between the effects, as contrasted with random effects. So in the fixed effects model, these yi's are not assumed to be related to each other in any way. They're just, you did a study, you got an estimate, somebody else did another study, they got another estimate. There's no necessary relationship between these at all. So there's no relationship between the theta i's. They can all be different. Every study can be estimating its own mean, can have its own variance. And so you might not even really care about what the average effect is in that case. You might just say, well, different studies got different estimates, and I'm just going to summarize descriptively what they were. But you might be interested, somebody might say, well, okay, even though, and let me take an example, let's say every study was done in a different country. Let's say you had one study done in every country in South America, right? There's no reason to believe that the study done in Peru is any related to the study done in Argentina, but somebody might be interested in, okay, well, what's the overall effect in South America? So you want to take some kind of an average. And so what you might do is you might just average these estimates. Now, because they're all unrelated, kind of the most obvious thing to do is just give them all equal weights. So you might just do an equally weighted average like we talked about in that case. All right? So that's what I'm going to call a fixed effects estimate. It's very uncommon that anyone does this, but it agrees with statistical terminology. Now, the next model is the common effect model. The common effect model assumes there is a relationship between the estimates in each study and the true means in each study. In fact, it makes a very strong assumption that the mean in each study is the same. All the theta i's are the same. They're equal to a common theta. So that's a pretty strong assumption. That means basically one way I think of that is if every study were infinitely large so that you had no random variation, they'd all come up with the same estimate. All right? So that's very different from the fixed effects model. Now, unfortunately, in the meta-analytic literature, that common effect estimate is often called a fixed effect estimate. But that does not correspond to, for example, what we think of as fixed effects in analysis of variance. If you do a one-way analysis of variance, fixed effects means that all the groups have different means, and you might average them together. But it doesn't mean that they're all the same. So we're trying really hard to get that terminology changed, but I just want to warn you because a lot of times when you read the literature, you're going to see it was a fixed effect estimate, and this is really what they mean as a common, all the means are assumed the same. Yes? Yep. Yes. Right. So yeah, a lot of those estimates are common effect estimates. However, I'm going to put this into a modeling framework. So if you assume that there's no between study variance, then you have a common effect model, and in that case, yeah, those estimates that I showed you there, those are actually estimates of the mean effect. They're not. You can still use. Okay, so let me step back. Let's say your statistic that you're using was a mean difference, right? So the individual statistic in each study is a mean difference. You're going to combine them together according to some model. The model might be that all of those mean differences are estimating the same mean. Likewise, I could have standardized mean differences and combine those all together to have the same mean. So the standardized mean difference is really the statistic I'm combining. It's not whether it's a common effect or a random effect. Okay? Just like I could have combined odds ratios. But I can have common effect odds ratio or random effect odds ratio. I can have common effects mean difference or random effect mean difference. I can have, so it's the average of all those statistics that I'm using. So you have to differentiate between the statistic coming from the study, which is like the odds ratio, or the average of those things, which is the overall meta-analytic estimate. Okay, so I'm gonna use a picture here. So the 4 rows here are 4 studies, and the blue dots correspond to the true effect in each study, the unknown true effect that you're trying to estimate. And because they're all the same, they're all equal to theta, this is a common effect model. Every study is estimating the same thing. You don't know what this estimate is. You're trying to figure out what it is, but they all are fundamentally the same. Now, each study is done, and there's a standard error associated with each study. So let's assume for simplicity that the standard errors are related to the sample size. So the first study is a little bit wider distribution than the second study because maybe it has a smaller sample size. And the third study is even wider because maybe it's a very small study, so it has a lot of uncertainty. So now I'm going to draw, yes?
Are those variations distributions of the samples, or are they estimates of the population?
This is the population.
Based on the sample size?
Right. So now I'm going to draw a value from this distribution. And this is what the light blue diamond is. So this is my observed value drawn from that true distribution. So sometimes I might draw above the mean, sometimes I might draw below the mean. And you can see that generally I'm going to draw within the range of the distribution. And so I get some variability. Now, remember that the blue circles are unknown. I don't know them. All I observe are the blue diamonds. So that's what I see, right? So you might look at that picture and say, well, those seem pretty different to me. I think there's heterogeneity. I think all these studies have a different distribution, have a different mean. But actually, in truth, they're all the same mean. The only reason that they vary is because of random variation. It's just statistical heterogeneity. So I'm going to take these estimates. These are my sample statistics, the estimates together with their standard errors, and I'm going to use my weighted average formula to estimate the mean, the common mean, and the variance of the common mean. Right? So the estimate of the common mean, mu hat sub b for common effect, is the weighted average. I'm averaging the yi's with the weights wi, which are 1 over vi, right? Or 1 over vi divided by the sum of the w1 over vi's to normalize them. And then I can figure out what the variance is as well. And so now that I have an estimate, I have mu hat and I have its variance, I can construct a confidence interval for that overall mean. So using that estimate and that confidence interval, I can now draw that diamond at the bottom of the forest plot. Okay? So the assumption here is that this is, all the studies are estimating the same mean, and I've estimated that common mean, and I've got a confidence interval for it. All right? So that's the standard common effect estimate. There's other ways that you can estimate the common effect. I've showed you sort of a least squares type estimate, generalized least squares. You can also use the Mantel-Hensel test. That gives you an estimate of the mean squared, or the Mantel-Hensel estimator. And there's also a Peto estimator as well, which I'm not going to get into, but you'll sometimes see these in literature. So these are all different ways of calculating the common effect estimate. And they just use slightly different weighting formulas. If you look up the Mantel-Hensel estimate, you'll see the weight formula there, and it's just a little more different. It's just a different way of doing the weighting. Okay, so that's the common effect estimate. Now we're going to go to the random effects model. So the difference between the common effects model and the random effects model, the common effects model assumes that every study has the same unknown true mean. The random effects model says that every study has a different unknown true mean, but that they all come from a common distribution. So in other words, the studies are exchangeable. Before I collect the data, all I know is that the mean I'm going to draw from that study is coming from some distribution. I don't know which one I'm going to draw, right? So they're all coming from the same distribution, which means they're exchangeable. So here's a picture. Let's assume that this distribution, which we'll assume is normal for simplicity, is now not the distribution of a single study, but it's the distribution of the true effects in multiple studies. So this is the distribution of the true means that I could see if I were to do a study. So if I do a study, I'm going to draw a mean from this distribution, right? So if I draw a small mean, it means that my study has a small effect. If I draw a large mean, it means my study has a large effect. And the reason that these effects might vary might be because they have different patient characteristics, whatever the heterogeneity is that might be introduced here. So I'm going to assume that the theta i's, now the true means are going to be, in each study is going to be theta I, and they're going to be drawn from a normal distribution, let's say with mean mu and variance tau squared. So they all come from the same distribution with one mean and one variance. So now my objective, I have two objectives now. I want to estimate mu, I want to estimate tau squared, and I also want to estimate theta I if I can. So now I draw now I get my true means, and now my true means are all different, but they're all from this distribution. Right? So remember, in the common effect, the true means were all the same. Now they're different, but they're from the same normal distribution. So now I run my study, and my first study here, my first study is drawn from this true mean, right? So I do my first study, and it turns out the true mean in that study is this number. Let's say it's 10. So that has a mean of 10, and it has a variance. And so here is my sampling distribution for that particular study. I'm going to take a draw from this distribution. The next study has a mean over here, so I'm going to take a draw from that distribution. The next study has a mean here, so I'm going to take a draw from that distribution. So now I have my blue diamonds, I get my draws. So I have two components of variation now. One is within study variation, and the other is between study variation. So if you'll notice, when I actually show you what I observed, these are more variable than they were in the common effect model, because this value differs from the overall mean here for two reasons. One is its mean is different, and the other is that there's random variation within. Right? So if I go back here, this value is different from the overall mean, both because this distribution is shifted over here, and then there's additional random variation. Two components of variation. All right. So the model is that each yi, each statistic that I calculate in each study, whether it's a mean difference or an odds ratio or whatever, has its own mean theta I and its own variance vi. I'm still going to assume the vi's are known. Okay? And I'm going to estimate, I'm going to use the estimate from the study as my estimate of those. So this is going to describe the distribution of the observed effect yi within a study centered about its true mean theta I with a usually assumed known within study variance vi. Right? That's the first stage. The second stage is that the theta i's, remember, they come from a distribution themselves. They come from a normal distribution with mean mu and variance tau squared. So this describes the distribution of the true treatment effects theta I. And if you put it together, if y is normal with mean theta I and variance vi, and theta I is normal with mean mu and variance tau squared, then overall yi has an average mean of mu, because, right, the average of these theta i's is mu, so therefore the overall average of the averages is mu, but the variance is a sum of these two variances. It's a within variance plus a between variance. Okay? Now we want to know how to estimate. How do we estimate mu and tau? So first of all, let's think about estimating mu. So remember before we said the weighted average we wanted a weight that was 1 over the within variance. Now we're going to use 1 over the total variance, which is 1 over v plus tau. So our weights now are 1 over v plus tau, normalized by their sum. And so now our weighted average is, again, it's just a weighted average, it's just we're using different weights. And we get a variance of that as well. Okay? Now, let's look a little more closely at that formula. Before we were weighting by 1 over vi, now we're weighting by 1 over vi plus tau squared. So if the between study variability is large relative to the within study variability, then tau squared is going to be big relative to v. And therefore, all these weights are going to be very similar because they're going to be dominated by tau squared. So if you have a lot of between study variability and very little within study variability, then that's almost like having an unweighted average because all the weights are the same. And why does that make sense intuitively? If all of my studies were huge, so that I had very little within study variability, I knew each study estimate very well, right? Now the only variability is between study. And since the studies are all big and I know them all pretty well, there's no reason to weight one any more than the other. I should weight them equally. Conversely, if tau squared is close to 0, then that means I'm really more like in the common effect situation, and I'd want to weight them according to their individual variances. So what this allows you to do is it allows you to kind of trade off between the within variation and the between variation. To the extent that the between variation is large, you weight the studies more equally because you believe the studies are all inherently different, and so therefore you want to weight them similarly to each other. If the between study variability is small or the within study variability is large, then you want to give more weight to the within study variance, not the between study variance, right? And then it would be weighted more according to, let's say, the sample size. All right. Now, the other thing is that if you look at this variance estimate here, it turns out that since this has got two components, this variance is actually bigger than the variance of the common effect estimate. And therefore, the confidence interval on the random effect estimate is generally wider than on the on the random effect estimate is wider than on the common effect estimate. And that makes sense because you've got more variability you're adjusting for. You're less certain about things because you're not estimating the same mean, you're estimating different means. And I'm saying, well, what's the average of all these different studies? But I don't believe these studies are the same, so therefore I have more uncertainty about what the true average is. Okay. Questions? Yes. Yeah, so the random effect variation includes two sources of variation, within and between. So it's going to be bigger than the variance of the within, which is just one component. Right? Let me see if I can think of a sort of an intuitive example here. Well, let's say I was interested in estimating the average height of a group of kids, and I had selected different kids in different studies, and I'd estimated their heights. So if all the kids in all the studies are pretty similar, and I got very similar estimates of height within each study, I'd probably be much more sure about what the average is than if I got very different estimates in all the studies, because then there'd be more uncertainty, because now the average is not just the average, I'm averaging different groups. And so intuitively, I don't know as much about it because they're different groups. Okay, so now I'm gonna talk a little bit about some of the assumptions. Remember, I mentioned earlier that one of the things that we want to be careful about in all these models is the assumptions on which they're based. So I've put a couple of assumptions in here which you may have picked up on, but one is that I've assumed everything is normally distributed. Another thing is that I assumed that I knew these within study variances. The VIs were known. So first, the normality assumptions here. First of all, these methods work whenever Y can be assumed to follow a normal distribution. So typically that will work pretty well when you have mean differences. If the means are calculated on large enough sample sizes, then the means will be normally distributed by the central limit theorem. This is also why we typically use log odds ratios rather than odds ratios, because they tend to be more normally distributed as well, or with a standardized mean difference. So these effects are typically normal as long as you have large enough sample sizes. So basically, if you have big studies, then you can these assumptions of normal distributions for the YIs are reasonable. But sometimes we'll have small studies, in which case those normality assumptions may not be as reasonable. And in particularly, the problem is that when the outcome is binary, you might be better off using the underlying distribution, like the binomial distribution, rather than assuming normal distributions of these things. Okay, so let's again look at the model. We have the yi is equal to theta I plus ei, or epsilon I, right? So theta I is the mean, and we're assuming that epsilon I is the random variation of mean 0 and variance vi. And theta I has mean theta and variance tau squared. So we're assuming here that yi is unbiased for theta I, because the expected value of epsilon I is 0. And we're assuming that the within study variance vi is known, in which we often use the sample estimate vi hat. And then if you want, you can put normal distributions on theta I and epsilon I. So that's the model that we've used. So with those assumptions, there's a nice paper by Dan Jackson and Ian White where they talk about what are the consequences of some of these assumptions. I'm going to just try to review some of that for you. First of all, the first assumption is that yi is unbiased for theta I. So there's an issue here that if you do a transformation, if it's a nonlinear transformation, then something which is unbiased on one scale is not going to be unbiased on the other scale. So for example, if yi as the log odds ratio is unbiased for the true log odds ratio, then yi as an odds ratio will not be unbiased for theta I as an odds ratio, right? Because there's a nonlinear transformation there. A second problem is that if you've got things like publication bias and reporting bias that we talked about yesterday, where we don't have all the data that were actually ever collected, or somebody only reported the significant studies, then again, there's going to be a bias involved, and now the yi might not be unbiased for the true theta I. So let me give you an example. Let's say that let's say somebody did a study and they randomized 100 people in each group, and some of the people dropped out from the study, and they ended up reporting the results for the people who remained in the study. And let's say instead of 200 people, that was 170 people. So you're missing data on 30 people. So the estimate you have of whatever statistic you're calculating is based on n of 170. The true effect, though, should be based on the full sample of 200. So that estimate of 170 may not actually be a good estimate of the true sample. There may be a bias there. In particular, if the people who were doing poorly dropped out of the study more than the people who were doing well, then you're going to have an overestimate of the effect. A second assumption is the within study variance is known, or that you have a really good estimate of it. So this is generally okay, again, if the studies are big. Because if a study is big enough, the sample variance or the sample standard error that you calculate from that study is going to be a pretty good estimate of the true one. But many studies are small. And so, for example, let's say you do a clinical trial and you have 35 people in each group, and you estimate the mean difference and you estimate the variance of the mean difference. That estimate may be not quite correct because it's you don't have enough data. So assuming it known may be problematic. There's another problem, which is that, as I mentioned earlier, when you're dealing with proportions, the standard formulas that we use for the variance of a risk ratio, a risk difference, and odds ratio involve the true proportion, right? So the variance, the delta method estimate of the variance of an odds ratio is a function of the true proportion that you're trying to estimate. All right. Therefore, the first problem is that the variance formulas are approximations. They're not true variances, right? They're large sample approximations. So again, if you don't have large samples, they may not be good estimates. Second problem is that they ignore the fact that the yi and the vi are correlated because they're both functions of the same parameters. They're both functions of the unknown probability. And so therefore, if the parameter that you're trying to estimate is the proportion or the odds ratio, and the variance is a function of that thing, then you can't say the variance is unknown if the parameter is unknown, right? So it's like, so in the normal, in the continuous case, it's okay because the mean and the variance are separate parameters. And so you can assume that if I don't know the mean, I can know the variance. But if you're dealing with an odds ratio and the mean of the log odds ratio estimate is a function of the probabilities and the variance is a function of the probabilities, then I can't assume that the mean is unknown, but the variance is known, right? Because they both involve the same parameters, which are unknown. Okay, so that's a definite issue. Again, in large enough samples, you might be okay. You might be able to get away with assuming the variance is known. Third assumption is that the estimates, the true means theta I and the random error is epsilon I, which is the conditional variance of y given theta, are normal. All right, so this is important because you need some kind of a distribution in order to get a confidence interval. You can get an estimate of the mean and the variance, but you can't get a confidence interval without some assumption of the distribution. So again, these assumptions of normal distributions rely on large samples because of the central limit theorem. But again, many studies are small. So if you assume that this distribution of y given theta is normal conditional on a known v, even if you assume the variance is known, then it can't hold conditional on the estimate v hat that you are assuming is the same. And so unless you assume v hat and v are the same, if you don't assume that, then this assumption can't hold either, because one is conditional on the true parameter, one's conditional on the estimate. And so there's no central limit theorem here that works for the normal assumption on theta I, because the theta i's, remember, they're being drawn from a distribution that's across the studies, but you generally don't have many studies, so you don't have large samples there. So there have been various suggestions that have been made for coming up with confidence intervals for meta-analytic estimates, and one of them is to use a t-distribution rather than a normal, because you don't know the variances. So therefore, in those cases, we use a t-distribution. So it's hard to identify what t-distribution to use, but I'll talk a little bit about some of those estimates. Okay, so that is, those are three assumptions, namely that y is unbiased for theta, that the variances are known, and that the distributions are normal. And so they all hold fairly well in large samples, because they're all basically based on asymptotics. But the problem is that a lot of times in meta-analysis, we have small samples. And so there has been a lot of discussion recently about, well, how accurate really are these estimates when we're relying on these large sample approximations? Okay. Now, there's another set of assumptions that we make, which is, first of all, that the estimated mu, whether it's a random effect or a common effect, is unbiased for the true mu. That the variance of this estimated mu is known, and that mu has a normal distribution. So again, the overall mean estimate of mu is not necessarily unbiased for the true mean if the yi's are biased, or if the yi's are correlated with vi, which, as we said, can occur. Because the correlations between the y's and the v's is going to induce correlation with the study weights, right? Because the study weights are based on the v's. And therefore, because you have correlation between the y's and the weights, therefore, mu hat is no longer, so remember, mu hat is a weighted average. So it's only unbiased if that's a weighted average of independent items. If the items are correlated, when you sum things that are correlated, you don't necessarily get an unbiased estimate. A second assumption is that the variance of the mean here is known. That should actually be variance of mu hat rather than theta hat. So standard methods assume that the variance of the pooled estimate is known because these involve vi, which is assumed known, and estimates tau squared, which are also assumed to be estimated without uncertainty. So for example, if I look at the variance of the common effect mean, mu hat, that's 1 over the sum of 1 over the vi's. If I assume the vi's are known, then I'm assuming I know that. Likewise, the variance of the mean of the mu hat for the random effects is 1 over the sum of 1 over the vi's plus tau squared. Again, I don't know, if I assume I know vi, and if I assume that I have a good estimate of tau squared, then I can assume that these are known as well. And then when I go to do my confidence interval, I just plug in those estimates, right? But if I don't know vi, or I don't know tau squared, then these are just estimates of these variances, and so therefore they're not very well known. And so when I plug them into the confidence interval, I'm ignoring an important aspect of them, which is that they're not known exactly. So I will tend to underestimate my confidence intervals because I'm assuming things that are known that really aren't known, right? So let's say I estimate tau squared to be 10, and I plug that into my variance estimate, and I come up with a confidence interval. That's the correct confidence interval if tau squared is 10. But if tau squared is actually an estimate, and it could be anywhere between 5 and 15, then there should be uncertainty in that confidence interval as well, because I don't know the variance estimate. A final assumption here is that mu hat is normal. And so, again, assuming normality, you can compute confidence intervals. And as I said, you might want to use a t-distribution to account for the uncertainty in your estimating of tau squared. But the problem here, it's like with the unequal variances t-test, it's hard to estimate the right degrees of freedom. And the t-distribution itself makes the normality assumption, which is that the data are coming from an underlying normal distribution, even though you don't know the variance. So for the common effect model, the normality of the estimate mu hat depends on the weights being constant or known, but we know they're estimates, and that's almost always ignored. For the random effects model, there's a model called the Hartung-Knapp model, which relies on a good estimate of tau squared, but you oftentimes don't have a good estimate of the between study variance because you don't have enough studies, right? So you generally need probably at least 10 studies to get a good estimate of the variance, but you often don't have that. So it's very surprising, actually, if you look in some of the large databases of meta-analyses, like the Cochrane collaboration, you will find that a large majority of the meta-analyses have fewer than 10 studies. And they just do meta-analysis of it. And they just kind of ignore the fact that, these things are not estimated very well. They pretend like they're known. And so they probably are all underestimating the uncertainty with which these things are calculated. So let me give you an example, because this is somewhat theoretical here. So let's say I want a confidence interval for the random effects mean. So I take the estimate plus or minus, and let's assume I can use the normal distribution, plus or minus a z statistic, let's say 1.96, times the variance estimate, which is 1 over the sum of the wi's, where the wi's are 1 over vi plus tau squared. So this is an accurate interval if the estimate tau squared that I plug in, tau hat squared, correctly estimated tau squared. If that's a correct estimate, this confidence interval is good. But since it's only an estimate, because I've estimated tau squared, the standard error is actually biased, and the uncertainty is not captured. And it's even worse if I assume the VIs aren't known. Deep within study variances are estimates as well. So, this confidence interval is basically a random variable itself. And so the estimate that you get may be quite low. So there's a way to kind of get around this. These 4 authors in sort of 2 independent papers came up with a way of sort of trying to correct for this. And this is based on the Q statistic that we talked about. So if the Q statistic, and I've changed notation here, so there's I studies rather than case studies before. If the Q statistic follows a chi-square distribution with I-1 degrees of freedom, and if we can assume that the difference between the estimated mu and its true mean divided by the variances is a standard normal distribution, then we can use the relationship between the chi-square and the normal to derive a t-distribution, and we get a t-interval with a t-distribution with k minus, switch back to k now. It's k-1 degrees of freedom, or I-1 degrees of freedom, times 1 over this expression with under the square root, which is the standard error. Okay, so this would be a corrected confidence interval, and you could compare this confidence interval to the one in the previous page, right? Which was which is z times 1 over the sum of the wi, square root of the sum of the wi's. We have now changed that to a t, and we've changed the standard error estimate. And this standard error estimate now corrects for the uncertainty in estimating tau squared. So it's somewhat approximate because you still are plugging in a tau squared, but at least it accounts for the fact that you've estimated the weights and you've estimated the variance. So therefore, it's got the right distribution. So this is typically a better estimate, and there have been a lot of simulation studies which have shown that this confidence interval has better coverage properties than the standard normal. So for the random effects model, the problem with the random effects model, as I said, is that we need the estimate of the between study variance tau squared in order to be able to get a good estimate of the random effects model mean. And we usually don't know that between study variance, and we usually have very few studies in which to estimate it. So this implies that the weights are unknown, And so the standard estimate that makes assumptions about known weights is also not accurate. So there are three issues. I don't know if they're controversial, but they're at least issues that are debated in the literature. How do we estimate tau squared? How do we construct confidence intervals? And how should the estimation of the weights be handled? All right, and so there's a large literature on those, and I'm just going to very briefly review it. Again, software will do these calculations for you, but you'll oftentimes find in the software all these different types of estimators, and you might be kind of wondering, well, which one should I use? So I want to just review a few of them to give you a sense of the differences. All right. So the estimators typically are either method of moments estimators or they're likelihood-based estimators. The advantage of the moment-based estimators is they don't assume a distribution. The likelihood-based estimators strictly require both within and between study normality assumptions, but they've been shown to be robust to those assumptions, so they work pretty well. The most common one is called a D'Arsimonean and Laird. Most software packages will do this by default, and most papers that I review use this estimator, I think because most of the people doing it don't really, they just use the default. They don't even really know what they're doing, but they're just plugging in an estimate. So the D'Arsimonean and Laird estimate is a moment-based estimator, and it's calculated as follows. You compute the Q statistic, and then you set the Q statistic equal to its expected value under the random effects model, and you solve for tau squared. And when you do that, you get this value here, which is Q minus K minus 1 divided by sum of the WIs minus the sum of the WIs squared over the sum of the WIs. All right, so that's fairly straightforward to calculate. You could do that in a spreadsheet. And if the value is negative, you force it to be 0. So that's like a lot of variance estimators, right? When you get negative variance estimates, you assume 0. Now, if you assume it's 0, then you're assuming the common effect model. And if it's non-zero, if it's positive, then it's a random effect model. And so that's the most common estimate, fairly simple to calculate. Hedges and Olkin have a slightly different estimator. They compute the sample variance of the within study estimates, ignoring their variances, and then set it equal to its expected value. And so their formula is fairly similar to the D'Arsimonean and Laird, but it basically uses Y bar here instead of mu hat. So whereas in the Q statistic, we're using mu hat, in the Hedges and Olkin, you're using Y bar. Now, Y bar is the unweighted mean of the Ys. So in essence, what Hedges and Olkin are assuming is that all the studies are weighted equally, whereas the D'Arsimonean and Laird is assuming that the studies are weighted inversely proportional to their variances. But in practice, these are very close to each other. A third type of estimator is called the empirical Bayes. So this is kind of an iterative estimator. You estimate tau squared using some estimator, say the D'Arsimonean and Laird. You then plug that estimator in to get the random effects estimate, mu hat RE. Then you recompute the Q statistic using mu hat RE instead of mu hat CE. Recompute weights, set Q equal to its expected value, solve for a new tau squared, and then you iterate on that. So now with a new tau squared, you can plug that in, get a new mu hat. You can therefore get a new tau squared, and you iterate that until convergence. And that's an empirical Bayes estimator. So that's a little bit better than the D'Arsimonean and Laird, because the D'Arsimonean and Laird only takes one step of that algorithm, whereas the empirical Bayes does multiple steps. And so that's been shown in practice to work better. There's other estimators too. So another common one is the restricted maximum likelihood, or the REML estimator. So you use the restricted log likelihood to adjust for negative bias arising in the maximum likelihood from failure to adjust for estimating the mean. And so typically, in very simple situations, the REML estimator is equivalent to using a sample variance with a divisor of n minus 1 instead of the n, which is the usual maximum likelihood estimator. And this tends to work pretty well with continuous outcomes. So the restricted maximum likelihood is generally used a lot. None of these variance estimators work really well if you have only a few studies. And there's lots of others too. There's at least, there's a paper a few years ago that compared about 15 of them. So, you know, I think Metaphor has 8 or 10 of these. And empirically, I don't think, if you've got large enough sample sizes or enough studies, it really isn't going to matter much. But there are certain circumstances where it will matter. So one of them is the Dersman and Laird has reduced coverage for mu hat when the between study heterogeneity is large. And what that means is that the confidence intervals will tend to be not really correct. They won't cover the true value often enough. And that's because they're too narrow. The confidence intervals are too narrow, and therefore they sometimes miss the true value. And that's because you're ignoring the uncertainty in estimating tau squared. If you think back to the empirical Bayes estimator, remember I estimated tau squared, then I plugged it in here to re-estimate mu, and then I kept iterating back and forth. So in essence, I'm using the estimate of tau squared to estimate mu, and I'm using mu to estimate tau squared. Whereas with the Dersman and Laird, I'm just using a one-step estimator. So I'm not accounting for all that variability. So the empirical Bayes estimator tends to work better than the Dersman and Laird in simulations, particularly for smaller sample sizes. And the Rummel method used works pretty well, but it's more computationally intensive. Okay, so that's sort of a rough overview. So I mean, I guess the takeaway message is if you're going to use something, probably the Rummel estimator is fine, or there's also one called the Pal-Mandel, which works pretty well, or the empirical Bayes. But a lot of times you can get away with a Dersman and Laird. And one thing you can do with software is just try them all and see if there's any difference, right? I mean, if there's a lot of differences between them, then you have to figure out which one to use. If they're pretty much all giving you the same answer, it doesn't really matter. So again, the only way we really know which of these is better is through simulation studies. And so there's some papers out there if you want to look at those. All right, so then the next question arises, we've estimated tau squared. How can we get a confidence interval for tau squared? And so the most common approach here, and again, there's a lot of different methods for doing this, is called the Q profile method. And the Q profile method basically says the Q statistic based on tau squared is just the W's times Y minus mu hat squared. That's the usual Q statistic. But now the W's are a function of tau squared. And so how you plug in whatever estimate of tau squared you have into this. And then the confidence interval is constructed to include all values of tau squared such that the Q lies between the critical values of a chi-square distribution with k-1 degrees of freedom, where k is the number of studies in the meta-analysis. So this is a profile likelihood type approach for those of you who are familiar with that method. All right, again, the software will calculate this for you. Okay, then the last topic here to cover, because a couple people have asked me this, is, well, what does the confidence interval on a mean mean? Does that have any relationship to the confidence interval that I should think about a new study? And so the prediction interval says, okay, if I've done a meta-analysis and I now want to use that meta-analysis to plan a new study, what should I expect the estimate in the new study to be? So the obvious answer is we should expect it to be the average of what the meta-analysis gave us, which is correct. But what's the variance we should expect in the new study? So you might remember from basic regression that the variance of a new observation has more variability than the variance of an average, right? Because I'm running this new study, and there's two kinds of uncertainty. One is basically what is the mean of that distribution, and the other is what is the variance of that distribution. So I have to account for both of those sources of uncertainty. And so if I want to get a prediction interval for a new study, and I've used a random effects model, my best prediction interval is to say the mean is centered at the mu hat RE, which is my estimate of the mean, and I'm going to use a T distribution with k-2 degrees of freedom, where the variance is tau squared plus the standard error of the mean, right? Because that's the two components of variance. I have uncertainty about what the true mean is, and I also have uncertainty about what tau squared is. And I can motivate that by assuming that the new mean is drawn from a model with the same random effects model I had before with mean, mu, and variance tau squared, where tau squared and VI are known, and the new mean is independent of the random effects estimate. And so therefore, when I plug these in, I have the variance of mu, and I have the variance of tau squared, and that's where I get that standard error. So this is one way of doing a prediction interval, and that's also sensitive to a normal distribution assumptions here, because I'm assuming that for both the mean theta I and the mean of the new studies. So let's say I've done a meta-analysis, and let's say I'm working on the odds ratio scale, and I find that the average odds ratio in the studies I've got is 0.8, which means I get a 20% benefit from the new treatment. I want to run a new study, and I want to get an estimate of what the new treatment effect should be. My best guess is that it's also a 20% effect. But let's say I've estimated that mean of 20%, that odds ratio, pretty precisely, so that I know it's, let's say, between 0.78 and 0.82. So I'm pretty sure that the true odds ratio is 0.8, but I'm going to run a new study, and I want to know what the odds ratio would be in that new study. Well, I can expect it to be about 0.8, but that doesn't mean I know it's 0.8, right? Because it's got random variation of its own. And so in that case, looking at this formula here, the standard error of mu hat would be very small, but I would still have this between study variance, because the fact that my study is different from all other studies, I could expect it to fall somewhere in that random effects distribution. All right, so which model do we use? Common effect model or the random effect model? So in general, most investigators these days prefer the random effects models, because they assume that there has to be heterogeneity between studies. Studies are not all estimating the same thing. And they're also more conservative because they give wider confidence intervals. And so it's not generally recommended that you test for heterogeneity and then use whichever model the test shows. In other words, if the test for heterogeneity shows that tau squared is 0, then you use the common effect, and if it's tau squared is greater than 0, you use the random effect. That's generally not recommended these days. We generally just go with the random effect model. But you should always determine your model based on scientific reasons. So for example, if you have a protocol that you run in 5 different locations, and you run the same protocol, then you probably should be using a common effect model, because there's no reason to believe that the studies would really have any different means, right? On the other hand, if you've got 5 studies in 5 different places, then probably a random effect model makes sense. Yeah. Yeah, so I mean, in effect, what I've given you is a 2-level model, but you can always have more levels if you want. You could assume that theta i's are dependent on covariates too. Yeah. So how do we interpret the random effect model? So one of the sort of unsatisfying things about the random effect model is that although it adjusts for uncertainty, and it is suitable for unexplained heterogeneity, if there's important covariates, it's not really telling you where that heterogeneity is coming from, right? It's just saying, well, I have less surety than if they were all estimating the same thing, but if I tell you that the true estimate is 0.8 plus or minus something, if I had covariates, I might be able to nail down when it was above 0.8, when it's below 0.8. So conventionally, the inference here is focused on the mean of the distribution, but if we want to know about what the result of a new study would look like, we should use the predictive interval, right? Which would be the mean plus or minus 1.96 times the between study standard deviation tau. Okay, so to summarize here, we've talked about how meta-analysis gives you a statistical summary of effects from different studies, usually based on some kind of a model. We've talked about the common effect model and the random effect model. And we said that the common effect model applies when you're assuming that every study is estimating the same thing. But it's more usual to have studies have some heterogeneity, they're estimating different things. And so a random effects model might be better to use in many cases. There are various estimators of the between study variance available, and the results can be sensitive to the choice of that estimator when you have only a small number of studies because the variance is not well estimated. And in general, the restricted maximum likelihood or the empirical Bayes estimators perform pretty well. So those are two that I would definitely recommend to use. Okay, questions? That was a pretty technical section. I think that the key message to take out of it is you do have the common effect model, the random effect model. There are these two sources of variation in the random effect model, and you have to be aware of the fact that a lot of these things are being estimated, and so it's probably a good idea to be as conservative as possible. Use the random effect model, use the T correction, and use one of these variance estimators that works pretty well, like the Remel or the empirical Bayes. And let the software do everything else. Okay. All right, so we'll go into the next section, which is the one-stage model. So I'm going to try to explain what the difference between one and two-stage models is. And I'm going to describe the one-stage model. It's a generalized linear mixed model, right? So just put it in the context of general statistical models, and then talk about how we interpret findings. So this is a much shorter section. So think about a binary outcome. Everything we've been doing so far relied on normal distributions, basically. And so I said that when you had a binary outcome, you oftentimes might use an odds ratio as your statistic in each study. And so we might use the log odds ratio because it's more likely to be normally distributed. But we also know that when the studies are small, right, the empirical log odds ratio is not necessarily a very good estimate of the true odds ratio. And so we might want to use a better distribution than the normal. Another issue is that the normal distributions require us to use weights. Those weights are dependent on variances. We know in the binary case that the variance is a function of the mean, which is unknown. So therefore, the variance is pretty much unknown too. So models that assume that we know the variances are probably not very good. So we'd like to kind of get rid of this whole issue of normality and relying on variances. And there actually is a way to do that. So if you have the 2x2 tables, then you actually have the sufficient statistics to form the likelihood under a binomial model. And so you can use the binomial likelihood for each group to get maximum likelihood or restricted maximum likelihood estimates for these estimates. And it's similar to logistic regression. So it's basically just like a mixed model logistic regression. And you can also do it in Bayesian models as well. So how do we do that? So let me first talk about the model if I'm going to assume normality, but I'm going to put it into the context of a hierarchical model. So the yi's now are the observed treatment effect. Like let's say it's the log odds ratio. The theta i's are the unknown true effects from the ith study. And the first level, again, assumes the yi's given the theta i's are normal, and they have a known variance, SI squared. If I wanted to, if the studies are small and I don't think the SI squareds are very accurately estimated, I could actually put a model on that. I could, for example, use, I could assume that they're inversely related to the sample size, and I could assume some constant k and use k over ni, where ni is the sample size, or I could put some kind of a model on that if I were Bayesian. But generally, we're going to assume the SI squareds are known. Then at the second level, we say that the theta i's are normal with mean theta and variance tau squared. And now we're going to be looking at this in terms of the population level parameters theta and tau squared. So the common effect model assumes that the theta i's are equal to theta with tau squared equals 0, and the random effects model assumes that the theta i's are different, and so that marginally yi has mean theta and variance SI squared plus tau squared. Okay, so that's the hierarchical model under the normal normal. Now, what if I wanted to actually use a binomial model? So now, I'm going to assume that Ri0 is the number of events in the control group. Remember, I have a 2 by 2 table, right? So I have number of events in the control group, number of events in the treated group, number of non-events in the control group, number of non-events in the treated group. So if I look just at the control group, the sample size is Ni0. I have Ni0 controls, and Ri0 of them got the event. Let's say the event is they died. So Ri0 died, and Ni0 minus Ri0 didn't die. And Pi-I0 is the true probability of death in the control group. Likewise, in the treatment group, we have Ri1, Ni1, and Pi-I1. So I have two independent binomial distributions, right? I have a binomial distribution in the control group, and I have a binomial distribution in the treatment group. These are now exact, right? Because I'm assuming these data are, these observations are independent, and they have the same, it's the same probabilities. Each person has the same probability in the control group, and each person has the same probability in the treatment group of an event. So these are exact distributions. So Pi-I0 is the probability of an event given that you're in the control group, and Pi-I1 is the probability of an event given that you're in the treated group. Now I'm going to add on to that model a model for the Pi-I0s and the Pi-I1s. So I'm going to assume that the logit of Pi-I0, which is the log of pi divided by 1 minus pi, is equal to gamma I. So that is the model for the control rate. And I'm going to assume that the logit of Pi-I1 is gamma I plus theta I. So in other words, the logit of the probability in the treated group is equal to gamma I plus theta I. So therefore, theta I is the difference in the logit of the first group and the second and the control group. So the difference between logit Pi-I1 and logit Pi-I0 is theta I, and that is the same as the log odds ratio. So theta I is the log odds ratio. It's the difference in the probabilities on the logit scale. And again, I'm going to assume theta I is normal with mean theta and variance tau squared. So now I have a model where the observed data, the counts in each study, Ri0 and Ri1, follow two independent binomial distributions, and I have an underlying random effects distribution for the theta i's that is normal. So it's a binomial normal model. So this turns out to be a generalized linear mixed model. In this case, it's a generalized linear mixed model where you're using a logit link and you have a binomial underlying distribution. And so you can fit this as a generalized linear mixed model where G here is the logit and the studies are the strata. And the gammas are the control rates in each study, and you can either treat them as fixed or random intercepts. If they're random, you, for example, might assume that they're normal with mean 0 and some variance sigma squared. And then the theta i's can either be fixed or random slopes. And we assume that the gamma I and the epsilon I, which are the variances around the thetas, you can either assume them to be correlated or uncorrelated. So there's a whole different set of generalized linear mixed models you can use here, depending on whether you want to, what link function you want to assume, whether you want to use fixed or random intercepts, fixed or random slopes, and correlate the slopes and the intercepts or not. So for example, if I have fixed study intercepts, then I have the logit of Pi-I0 and the logit of Pi-I1. I put them together. They follow a bivariate normal distribution with means gamma I and gamma I plus theta as the means. And the variance of Pi-I0 is 0 because I'm assuming the gamma i's are fixed, but the variance of gamma I plus theta might be tau squared because I'm assuming the theta is random. All right. Now, one problem with this model is that as you get more and more studies, right? So each study here is contributing 2 observations. But as you get more and more studies, every study adds a new gamma I, right? It also adds a new theta I, but since theta I has a distribution, all you care about are the fact that it has 1 theta and 1 tau squared. But you get a different gamma I for every study, and therefore, this turns out to violate one of the conditions under which maximum likelihood estimation works, namely that the number of parameters is not growing with the sample size. So maximum likelihood estimates are asymptotically normal under the assumption that the sample size is growing faster than the number of parameters, but in this case it's not. And so this can lead to a negative bias in tau squared. And so there's a lot of work going on right now looking at these different models. But this is the standard model to assume that the intercepts are fixed, because what we're basically assuming now, if you think about the two-stage model, what we did in the two-stage model is we calculated, let's say, the mean difference in each study, and then we analyzed those mean differences. So we completely ignored what the control group mean was. All we worked with was the differences, right? So in essence, what we're doing is it's like a conditional model. We're conditioning on the control rates that were observed, and we're kind of ignoring them. So this fixed effect model basically says, all right, I'm going to estimate those control effects, but I'm going to assume they're different in each study. The gamma I's are all different. So in essence, this model is very much like the two-stage model, but it's assuming that these intercepts are fixed. And so therefore it has this problem of potentially negatively biasing the between study variance. Now this model has been used probably more often than any other, and one of the reasons is because it's felt that it protects the randomization. If you're combining randomized trials, then you know that the estimate that you get in each study of the treatment effect is unbiased. And so by just combining the estimates and not worrying about the control rates, you're sort of conditioning on the control rates, and you're in essence you're treating them like nuisance parameters. You're kind of integrating them out, and so they don't contribute to the estimate. So the estimate is now a combination of randomized effects. So now let me show you the model where you don't assume that the gamma I's are fixed. In that case, if the gamma I's have a mean gamma, then the bivariate normal distribution has mean gamma for pi I0, mean gamma plus theta for pi I1. But now your variances are a combination. So sigma squared is the variance of the gamma I's, and tau squared is the variance of the theta I's. And now you have these correlations, right? Because now the gamma I's and the theta I's are going to be correlated. And so the difference is no longer independent of, modeling the control group effects here may lead to leakage of information, because what happens is that if I assume that both the control rates and the treatment effects are coming from these common distributions. So let's say I have a study where the control rate is higher than it should be, higher than it's expected by random chance. Therefore, on average, the treatment effect in that study will be lower than it should be because the control rate's too high, right? And so that biases the treatment effect, which is the difference between the treatment rate and the control rate, down. So studies with large control rates have small treatment effects. Studies with small control rates have large treatment effects. So therefore, if I estimate the average control rate and I shrink the study estimates, the study control rates back toward the average, then that's going to change the treatment effects, right? Because now those small control rates are being shrunk back to the average, so their large treatment effects are also going to be shrunk back toward the average. And so now the estimating the control rates is going to affect estimating the treatment effects. And so now you basically have this issue that you no longer are just averaging the estimates from the studies that were unbiased. You're estimating the studies together with the control rates. And so this correlation is now affecting both sets of parameters. Okay, so this can be an issue as well. So you've got problems sort of either way you do it. In the one case, you've got these problems with the potential asymptotics not kicking in, and the other one, you have this leakage of information. And again, this is sort of a new issue that people are working on. In practice, it may not make a lot of difference if your sample sizes are big enough, but it can affect things in some studies. Okay, there's other ways that you could write these models. And so again, there's a nice paper by Jackson and White and a couple of other people where they talked about different ways of parameterizing these models to try to control for some of these effects. So you could actually write the model as the logit of the probability is gamma I plus theta times zi plus zi minus 0.5 times epsilon I. So this is just sort of a transformation, changing the, in this case, centering the treatment effect on 0.5 rather than on 0. And then you get a slightly different normal model. And this model, apparently, according to some simulations that they've done, doesn't negatively bias tau squared. So basically, you're transforming your predictor, you're centering your predictor, and by centering the predictor, you remove the bias. So this is, again, a common situation in hierarchical models. It's always a good idea to center your predictors because it removes some of the correlations that can cause problems. And similarly, you can do it with random study effects as well. Another way to do the issue, let's see, I went the wrong way there. Another way you could do this is as a bivariate model. So you could actually set up the two logits to have a bivariate distribution, and then you have to estimate the correlation between the two. This generalizes the previous models because the previous models have put constraints on the covariance structure. So for example, back here, we have the variant, well, let's go back here. The variance here is sigma squared and sigma squared plus tau squared with a covariance of sigma squared. Here, this is sigma squared, this is tau squared. And this is a general model with a general correlation rho. In the other model, this assumed that these two were the same, and this correlation was 1. So there were certain constraints on these parameters. Again, these models can be fit in some of the software packages. And then finally, there's a hypergeometric model. Again, if you want a condition on the total number of events, to create a mixed effects conditional distant regression model, you can figure out that this probability here of the number of events in each group, conditional on the true mean, follows a non-central hypergeometric distribution, and so forth. And you can get conditional likelihood ratios for that. And then if the events are rare, that can become a binomial model. So again, I'll give you this. You've got the slides. You can sort of look through this on your own. I know for some of you, this might be something that's familiar, and for other people, probably haven't seen this before. The point here is that there's a lot of different ways of doing these models, and they fit into sort of standard statistical modeling, but under certain assumptions, like that variances are known, and that you're using the variances as weights and so forth. But the nice thing is that because it's now recognized that these meta-analytic models are just special forms of standard statistical models, you can basically use standard statistical software to fit any of these things. And you can try various models out and test all these different assumptions and see which ones make most sense. The final point I just want to make here is that what do we do with the zero cells? The zero cells can be problematic, as I said, because in the two-stage model, we can't calculate the variances because we get these zeros in the denominators. If you have studies that have zeros in both arms, in other words, there's no events in either group, then you get, let's say, for example, there are 0 events out of 20 in both the treatment and the control group, then some people would argue that those studies provide no information about your estimate, and they should be discarded from your meta-analysis. Just throw them out. This actually makes sense under some of the models, because if you do the calculations in some of the models, they're not contributing at all to the estimate. They basically get zeroed out. And the reason for that intuitively is, let's say you're calculating a relative measure like a risk ratio. So you want to calculate what's the probability of events in one group relative to the probability of events in the other group. Well, if I have 0 events in either group, that's not contributing any information to that, what that ratio is, because it's giving me a 0/0. I don't get any information about the ratio from that. So it would make sense there to drop it. Whereas if I were using a risk difference, then 0 versus 0 actually is providing me information, because now I'm saying the difference is 0. So in the relative measure, 0/0 provides no information. In the absolute measure, 0 minus 0 does provide information. Now, if you're using the binomial model, then the likelihood actually provides information, not about the odds ratio, but it does provide information about each probability. So if I'm interested in estimating the probabilities, if I ignore all the studies with 0 arms, then I'm going to inflate the probabilities that I'm estimating, right? Because I'm throwing out all the studies with no events. So while it's not helping me estimate the relative measure, it is helping me estimate the individual proportions. And so some people would argue that basically you should leave these in there, because the probabilities are also parameters that you're interested in. If you use a Bayesian method, then you can put all of this into prior distributions, and you can actually sometimes come up with answers that might be a little bit different, because they're going to rely on the prior information. And I'll talk about that later when we get to the Bayesian modeling. All right. So just to kind of summarize here, the nice thing about the one-stage models, which you might think of as generalized linear mixed models, and they're commonly used in the binary cases. They're nice because they avoid the problem of having to assume normality, and they also avoid the problem of having to estimate variances. Right? There's no variance involved in any of those binomial models within study variance, right? Because you're assuming a binomial distribution. So you don't have to make the problematic assumption that the variances are known. Another nice point about them is that, as I said, they're all generalized linear mixed models, and so you can fit them with standard software. There are a lot of different forms of them, but the main choice is between fixed and random study effects. So the gamma i's, whether they're fixed or random, that's the main thing that you have to choose. And it's not really clear which is the best way to do it, although it's more common to choose fixed study effects. Because the random study effects may compromise randomization and cause treatment effects to be affected by shrinkage of the study effects. However, the fixed study effects may bias the between study variance estimate. And so as again, we're sort of trying to work on when that can occur. And you could also use a conditional logistic regression model if you want. So these are just basically fancy logistic regression models in some sense. Okay. Question? Okay, so stage one is within a study, you calculate an estimate of some statistic like a mean difference, and you calculate its variance, and then you plug those into a weighted average, which is stage 2. Okay, that's stage 1 and stage 2. So stage 2 is just doing the meta-analysis of those estimates that you've got from each study, the weighted average, let's say, right?
So stage 1 is just doing what we normally do
For in each study.
Stage 2 is just going on to that.
That's right.
When you go from a typical algebra to do weighting, that's stage 2.
That's right. Now, the one-stage model, if I go back here to my slide, see in the one-stage model, I'm assuming that the counts are binomial distributions and the thetas are normal distributions, and then I'm fitting a generalized linear mixed model. So I'm not actually calculating anything within study and then plugging it into a meta-analysis for me. I'm doing it all in one model. So that's why it's a one-stage model. Okay. Yeah, so basically, you know, in a conditional logistic regression, you typically, let's see, where did I have it here? I guess here. You typically, in a conditional logistic regression, you have strata, and then you condition on, basically, you kind of have like matched pairs, and you condition on those matched pairs. So if you think about the meta-analysis, it's got these study effects, right? Because you have every study, and then it's got and it's got the estimates of the treatment effect within study. So the study effects are in essence kind of nuisance parameters that you have to estimate. And if you think of them as fixed effects that you're just going to condition out, that's sort of equivalent to doing a conditional logistic regression, because you're getting the estimate conditional on the gamma i's, which you're just estimating. You're not even really estimating them, you're just controlling for them. So typically the way you would do this is, you assume that, let's see, I have them here. That I have maybe I didn't put it in. Oh, so you're conditioning here in the hypergeometric model, which is like the conditional logistic regression model, you're conditioning on the total number of events in the study. So you're saying basically what's the probability that if I had 20 deaths in this study, that 7 of them would have been in the treatment group and 13 would have been in the control group. So conditioning on the 20 events, in other words, fixing them, I'm not going to actually estimate the overall prevalence of death in this. I'm just going to estimate the relative prevalence in the two groups. That's like I've sort of fixed the gamma i's in some sense, and all I'm estimating is the difference. All right. Okay. All right. Let's do yes. Question. Well, so the random slope model is basically the random effects model, right? So you're assuming that the treatment effects are random. The random intercept model says that all the studies. So basically, one way to think about a random intercept is what's the rate of events in the control group, and if you assume that the rate of events in each study is different and unrelated, then you have a fixed intercept model. And if you assume that they're related and coming from a common distribution, then you have a random effects model. Okay, which slide? 20, okay. This one? Okay. So, right, so the theta I can either be fixed or random. If they're fixed, it's like basically assuming the common effect model, because you're assuming all the effects are the same. And if it's random, then it's like the random effect model, right? Yeah, so I mean, typically I would always use a random slope model. If I used a fixed slope model, then that would mean that the slopes are fixed effects, like the model I talked about in the beginning, where they're just unrelated to each other. But that would be a little hard to work with. So I mean, I think you could treat the theta I as fixed or random, or you could assume the theta i's are all the same. So I probably should say common or random. They're all equal or random. Because you might think that, well, the underlying rate of events in the control groups are different in every study, but the relative effects of the treatment are the same in every study. So that would be a model with one common slope, but different intercepts. So like in a proportional odds model or something like that, you would have a similar type of situation. Right, where you're assuming that the rate relationship between the groups is the same in each study, but the underlying prevalence of the disease, let's say, varies from study to study. So, I mean, let's say, for example, your studies were let's say your studies were stratified on age, and so the the gamma i's really represented the underlying rate of events for people of different ages. You might expect people who are older to have more events than people who are younger. So the gamma i's would vary from study to study. But the underlying treatment effect, which is like, well, if I treat these people, let's say I'm looking at the effect of aspirin on a headache. And I assume that basically aspirin has the same relative effect on headaches for everybody, but people get headaches in different amounts. And let's say it depends on their age. Then I would expect that the intercepts would vary, but the slopes would all be the same, because the slope is the relative effect of aspirin for people who got aspirin versus people who didn't. So every study has the same effect, so it's a common effect, but every study has an underlying different control rate or an underlying different prevalence. So that would be a situation where you might have fixed or random intercepts, but you'd have a common slope. But in other cases, I might have random slopes, because I might assume that that effect varies from study to study. Okay. Okay. So let's see. We're at Tammy. What time do we want to stop for lunch? Okay. Yeah. Why don't we actually stop now and take a break, because I'm at the end of a module and we've been going for quite a while and pretty heavy stuff. So what I'm roughly halfway through the slides here, so it's actually pretty good. We'll start in the afternoon then with meta-regression, which will be a little bit less technical, and then we'll move on to the Bayesian modeling after that. So it is 11:53. What time do you want us back? Okay. So 12:50.